welcome to MPC Retreat. I have just one slide to open the event, so let me go over them. So the very idea of this workshop is somewhat new, not just to community but also to the country. And essentially the idea is that instead of having a large workshop with many parallel tracks and hurried conversations, we wanted to create something more focused and reflective. In other words, we wanted to create a space where the ideas can actually take root. So the goal of this retreat is not just to learn about new ideas, but to ignite ideas. That's the goal. So as you see from the program, we have carefully curated a bunch of topics across different aspects or facets of multi-party computation, and each talk is going to serve three things. At least that's the idea, or from the organizer side. So first, give a quick overview of the area. Second, highlight one or two key techniques which have driven the progress of that area. And third, and perhaps most importantly, is to lay out the very important open questions which are left. Okay. So if this retreat works the way the organizers imagine, then sometime in the future you will look back and you will say, that idea, that collaboration, that paper, it all started here. So that's the perspective that we have. So with that spirit, I wish you all a very happy MPC retreat. So enjoy the topical rain of talks, questions, and of course the ideas. And that's it. Thank you. And we'll start with the talks. Now you can applaud.
Good morning, everyone. I am Varsha from IIT Tirupati, and I'm here to deliver the first talk on, or the first part of the talk on secure graph computation. So I'm really glad to have had this opportunity to discuss about some of the key works that have happened in this direction of secure graph computation. Since this is the first opening talk, and it's 9:30 and you've just had breakfast and come, my aim is to not bore you down with a lot of details, but at least the objective that I have is I'll discuss some of the key ideas that have taken place in this domain, and my collaborator Bhavish will give the second part of the talk, which will be focused on discussing the state-of-the-art works in this area. So at a high level, what I want to deliver by the end of the talk is you should at least know some of the key things, like Arpita ma'am said, some of the key ideas that have allowed progress in this particular domain. So without further ado, let's just start. So I don't think I have to give motivation for why graph algorithms are important to be studied. So I'm sure all of you know ample of examples where real world applications are modeled as graphs, wherein you have a real world system and the entities in the system is modeled as a node, and the interaction between those entities is captured via an edge. So that's what I mean by modeling a real world system as a graph. And in order to understand some behavioral aspect about the system, what is usually done is you run several graph algorithms, for example, BFS, DFS, PageRank, etc., which allows you to characterize some aspect about the underlying system by analyzing the structural properties of the graph that represents the system. So graph algorithms, for example, you could, I'm sure everybody has already seen a lot of algorithms that rank different nodes in a graph when you're given a social network, and analysis of how information or disease is spread on a contract network or a communication network, etc. Some of the commonly used examples. So I think with respect to motivation, I don't need to spend a whole lot of time. But then the question that should arise is, okay, we've seen graph computations, but what do we mean by secure graph computation? So the idea is that most of these graphs house sensitive information. For example, in case of a social network, who are you friends with? Or in case of a contact network, who have you come in contact with? Or in case of an communication network, who are the people who you communicate with? Could actually be sensitive information. In fact, I can go ahead and say that in many scenarios, the graph that you deal with might be distributed across multiple data owners. What do I mean by that? The global picture of the graph could be distributedly held in such a way that each party only sees some local view, and what we wish to analyze is the global graph, right? And this becomes a challenge when the graph has sensitive information where data owners don't really want to disclose their share of the data to one another, but all of them are collectively interested in analyzing the global graph. So that's what we mean by performing secure graph computation. So as you might have already guessed, what we rely on is cryptography for the rescue to address this problem. There are multiple flavors in which secure graph computations can be looked at, but what will be the major focus for this part of the talks will be what we call as secure collaborative graph computations. And just to give you an example of what we mean by this, let me take the example of a transaction network. The different data owners in this setting would be the different banks, and vertices in this graph would represent the different bank accounts, and an edge between two accounts, as you might have already guessed, denotes the transaction or the financial transaction that's happened between the bank accounts. So there's a global graph that might be required to be analyzed, for example, to talk about fraud detection or to identify which nodes could be fraudulent, or it could be something as simple as or as complicated as analyzing the behavior of different bank accounts and associating some risk associated with every account. So for you to be able to analyze this graph, you need the picture of the global picture of the transaction graph, which means ideally all the banks should get together and disclose their individual view of their local graph and analyze the global picture of the graph. So this is what we mean by collaborative graph computations, because there are multiple data owners who wish to collaborate and analyze the underlying graph. Okay. So since this is about MPC, we basically look at MPC based solution or secure multi-party computation based solutions. So since this is the first talk, I'll still give the standard slide which describes what MPC is all about. So designing MPC protocols entails coming up with a protocol that allows different parties to jointly compute some function on their private inputs. And the properties that we wish to guarantee are firstly privacy and or correctness, and then privacy. What do we mean by correctness is that whatever the parties obtain as a end result of the protocol should in fact be the correct output of the underlying function. So in the case of graph computations, for example, if you're interested in computing the page rank of all the nodes, at the end of the protocol, the output that is generated should in fact be the page rank values of the different nodes in the graph. And what do we mean by privacy guarantee? We want to ensure that the parties who run the protocol learn nothing apart from whatever is the function output. So I'll talk about what are the privacy goals in just a while with respect to this particular application. But this is the high level idea of designing any MPC protocol, and we stick to the same. And in fact, just as other MPC protocols, we want to ensure these guarantees are provided even when there is even in the presence of an adversary, in which, I mean, what do I mean by that is that even if the parties deviate or misbehave, we want to guarantee at least correctness and privacy. Okay. So if I talk about MPC based, goals with respect to secure graph computation, the first goal is that of privacy. What do we mean by privacy when we talk about secure graph computation is the following. As I said, the graph houses sensitive information. So every node and every edge in the graph could be attributed with some sensitive information. For example, it could be attributed with some weights. Nodes can have weights, edges can have weights, and that is what we want to regard as sensitive information, and we want to protect that. And in general, we also want to hide the topology of the graph. What do I mean by this is that in almost all of the works, the underlying assumption is that the set of nodes that constitute the graph is always publicly known. What we want to hide is the presence or absence of an edge, which is essentially what captures the topology of the graph. So we want to hide the topology and the attributes that could be sensitive with respect to all the nodes and edges. The nodes that are part of the graph are always publicly known. It's the presence or absence of an edge that we want to hide. Since most real world graphs deal with a million node graph, or a graph that has million nodes and billions of edges, we want to design protocols that are scalable and efficient. So in order to design that, the three common goals, when you're designing MPC protocols, not just with respect to graph computations, but the goal of minimizing the rounds, communication and computation remains the same. Just to give you an idea, what do I mean by rounds? So we have an MPC protocols are designed as interactive protocols, which means parties communicate with one another. So we want to minimize the number of interactions or the number of sequential interactions that the parties are associated with. And we also want to minimize the communication cost, which essentially captures how much amount of data is being communicated between the set of parties. And the third goal is to minimize the computation cost, wherein each party performs some amount of computations locally, and even the local computations is something that we want to minimize. So overall, the best possible scenario is to get the minimum number of rounds with minimum communication and minimum computation. So we'll see as we discuss all the works that have happened so far. They basically look at different trade-offs between rounds, communication and computation, which will become clear as we go ahead. Okay, I hope the underlying problem of secure graph computation is clear. So since this talk is majorly focused on discussing some of the key ideas that have already taken place, let me begin by stating that secure graph computations has been looked at with respect to different flavors. So it's either looked at in the standard client server setting, or what is known as in the outsource setting, or in the non-outsource setting. For major part of the talk, or in fact for this particular talk, we'll be focusing on what is known as outsource and the non-outsource setting. We don't really focus on the client server model, but just to give you a picture of it, we'll go over each of these settings so that you have an idea of what are all the different flavors in which secure graph computation can be looked at. So the first setting is what is known as the client server setting. As the name suggests, this is a two-party protocol wherein the assumption is that the entire graph is held by a client, right? And the client is assumed to be a lightweight client, which means the client is assumed to be incapable of running heavy computations on a large graph. So what the client wants to do is it wants to outsource or give its underlying graph to a powerful or computationally powerful server, which will perform the computations on behalf of the client, right? And the goal here is that the server, when performing the computation, should not learn anything about the graph. So the graph algorithm will essentially, or any graph computation will basically be looked as a interactive protocol between the client and the server, where the client raises certain queries and the graph is stored at the server performs the computations on behalf of the client and gives back the results of the query. So whatever are the computations done at the server level, server should not learn anything other than the total number of edges and the total number of vertices, let's say, in the underlying graph. So there are multiple works that have been looked at in this flavor as well, wherein mostly the techniques revolve around designing secure protocols using what is known as an oblivious RAM or oblivious random access memory protocols. Where the idea is that the server stores this entire graph in its memory, and you want to ensure that the way these entries in the graph is accessed is done in an oblivious manner, which means the accesses should not leak anything about the structure of the graph. There are also some of the protocols that have been looked at in designing protocols specifically for the TEE setting, which is trusted execution environment, where the idea is that you run the protocol in a trusted processor, wherein the computations that happen at the processor is not really accessible to an adversary. And there are some works that look at combining both of these, wherein you consider a combination of ORAM based approaches and TE based approaches. So we won't be getting into the details of this, and what we'll be majorly focusing on is the outsource setting and its counterpart. Yes.
So how do they keep the graph encrypted, or
Some of them use encrypted. I mean, they encrypt the entire graph and then give it to the server.
under what kind of encryption?
Homomorphic encryption schemes are also there. Is yes.
Then they can't do any kind of
Uh,
It depends on the TE that you mentioned, right?
correct.
So if that is the TE case, then
So if it is yes, if it is just a TE based approach, then it doesn't matter.
TE,
A secure enclave.
enclaves, yeah.
Yes. Yeah. Okay. Yeah, coming back, for both the parts of the talk, we'll be majorly focusing on the outsource setting and its counterpart, which is the non-outsource setting. The idea of an outsourced setting is as follows. There are multiple parties or multiple data owners who collectively have the global graph, wherein each data owner has just a partial view of the graph. What they're interested in is in computing some graph algorithm on the global graph. So what they do is, rather than performing the computations on their own, they hire some small set of servers. It's also called MPC protocols in the small party setting. So the idea is to hire a small set of computationally powerful servers who will run the computations on behalf of these clients. And the goal is still the same, that the server should not learn anything other than the output. They should not learn the input or the output. So in case you're for example, if you're dealing with a secret sharing based approach, then the servers obtain secret shares of the graph and the servers send back secret shares of the output, so they don't learn anything. So it's just that the computations are outsourced to the servers. And this setting, again, similar to your client server setting, does facilitate having lightweight clients because the computations are outsourced to the servers. In comparison to its counterpart, which is the non-outsourced setting, which I'll come to in just a while, the outsourced setting is known to be more efficient because you have a small set of parties. So you run MPC protocols in the small party setting, which means you can have customizations designed specifically for the setting, and which makes them much more efficient. But the key idea here to note is that this offers a weaker notion of privacy as compared to the non-outsourced setting, which I'll come to. The reason being that each of the data owners here are expected to give up on their data either through secret sharing or through encrypting the underlying graph, but they rely on the security. I mean, the security of the protocol relies on the fact that the servers won't collude, right? It is because you're no longer in control of your data, you're not the party who's performing the computations. So the security depends on the threat model that you assume for the underlying servers. Before I talk about the non-outsourced setting, maybe I'll quickly try to give the overview of all the works that have happened in this direction in the outsourced setting. So, one of the key works in this direction of secure graph computation was a generic framework called GraphSC. The idea here was that so GraphSC is basically a framework that allows you to securely compute any graph algorithm, which can be expressed as what is known as a message passing graph algorithm. I'll come to what is a message passing graph algorithm in just a while. But at a high level, the idea is that the graph algorithm can be decomposed into primitive operations where a node sends some information across the edges and the node gathers some information across the edges and aggregates this information and maintains state, and this is done over multiple iterations. So that's what essentially a message passing algorithm is. So this framework called GraphSC designed a generic framework that allowed you to compute any graph algorithm that can be expressed as a message passing algorithm. But the important note that or the important observation that the work did is that most of our real world graphs are known to be sparse, which means the total number of edges are almost of the same order as the number of nodes. So rather than operating using the traditional adjacency matrix based representation, the idea was to represent the graph using a compact list. This is one of the works which we'll open up. So we'll see all the details of this work. But the idea was you operate on a list-based representation of the graph, and the framework relied on the popular approach of a garbled circuit-based approach to design the or to compute the underlying MPC protocol. So because it was a garbled circuit-based approach, the rounds was never an issue, but the communication and the computation overhead was very high. So as a follow-up, Araki et al. Proposed an improvement over this framework called GraphSC, where the observation that they made was to move from the garbled circuit setting and to sort of look at designing protocols in the secret shared setting. So they continue to operate on a list-based representation of the graph, but then rather than using a GC-based approach, they secret shared the graph and designed protocols that continue to operate on the message passing paradigm. But since we moved to the secret sharing based approach, so definitely if you move from a GC based approach to secret sharing based approach, you are expected to see an increase in the round complexity. But what they saved on was in the communication and the computation complexity. In fact, to achieve the best of both worlds, the work by Araki et al. Also proposes a round optimized variant, which ensures that you can parallelly process the list in such a way that the operations can be parallelized essentially, which allows you to reduce the round complexity further. So what we asked was, can we get the best of all and optimize the rounds as well and improve the communication and computation complexity? And one of our works called Graffiti primarily addressed the same. So we continue to be in the secret sharing setting itself, and we continue to operate on a list-based representation. But what we observed was that some of the operations that are required can be optimized, and of course the details of what exactly are the optimizations my collaborator Bhavish will discuss thoroughly. So the idea was, since there are some repetitive operations that are happening, there was some optimizations that we could introduce which allowed us to reduce the round complexity even further and without actually hampering the communication and computation complexity. Yeah. So this sort of marks some of the works in the outsourced computation setting. Okay, another side note, just so that you are informed. So all these works that I have just now listed are generic frameworks, wherein the idea was to propose some framework that will allow you to compute any graph algorithm, right? There are several other works that I haven't listed in this timeline, which have looked at designing graph specific MPC protocols. So given that they are tailor making the protocol for some specific application, they optimize the protocols for the application and achieve better efficiency. So there are application specific protocols also that are designed, which I haven't really included here, because the idea was to capture generic frameworks that can facilitate secure graph computation. Okay. So the counterpart to our outsource setting is the non-outsource setting, and as the name suggests, here the assumption is that you don't really hire powerful servers to run the computation on behalf of the clients, but the clients themselves participate in the protocol to run the underlying MPC protocol. So when we talk about the non-outsource setting, it's in general the aim is to design an n-party protocol, because you could have a setting where there are n parties which distributedly hold the graph, and this becomes slightly more expensive because now you are moving to a setting where there could be arbitrary number of parties when you move to the n-party setting. So as opposed to your outsource setting where you had small set of parties, this is more expensive. And naturally, since the clients are themselves expected to run the protocol, this can no longer support lightweight clients. But the upside of this is that it provides stronger privacy. Now, because you're not really secret sharing or distributing your input to hired servers, so your data remains with you. You don't really give out your data because you're running the protocol yourself. So, which means you have stronger notion of privacy or stronger guarantees, because as long as you don't collude, you're guaranteed that, I mean, you can design a protocol such that as long as you don't collude, you're guaranteed that your data is private, right? Unlike the outsource setting where you will have to rely on the guarantees provided by the servers. Okay. In the non-outsourced setting, there are again many works that have looked at designing generic frameworks. So one of the works that was first there is by Egmont et al. So the idea here was to actually look at the specific application of anti-money laundering, and they designed a protocol which is not really MPC based but a HE based solution. But HE based computations are known to be very expensive. So although the rounds was lesser and the communication was less, the computation cost involved in running the protocol is very, very high. The state of the art, I think, up until 24 in the n-party setting was a framework called CoGNN, where this again is still in the MPC, it designs an MPC based protocol in the secret sharing setting itself. And it has a higher round than the HE based solution that was there previously. And but the communication and the computation cost is much lesser. But the drawback of this framework was that the collusion threshold is just 1. So I won't get into the details of the protocol, but essentially what the protocol did was the entire computation was broken down into multiple two-party protocols. So you had two parties which would run the computation, which means as long as even one party decides to collude, then your secrecy or the privacy guarantees no longer remain. So the threshold collusion being, the collusion threshold being just 1 is a very, very bad drawback. In fact, our own work that I discussed in the outsource setting, which was Graffiti, can actually be instantiated even in the n-party setting. But it comes at the cost of higher number of rounds, because now the number of rounds, communication and computation are all dependent on the number of parties, because you've now moved to the n-party setting. but it gives you better collusion threshold, because now we can guarantee that as long as there is at least one honest party, then you're guaranteed privacy. Um, we also have one of our recent works which is called Grasp, which essentially looked at improving. So the idea that we had was graffiti was never designed for the non-outsource setting. It was specifically designed for a small party setting. So we thought, okay, can we look at optimizing the protocols when we know that the underlying protocol is going to be instantiated in the end party setting. So that's when we designed the framework called Grasp. So leveraging the fact that the graph is distributed and that there are n parties, we were able to design protocols that have compared to all other works, it has the minimum number of rounds and communication and computation as well. As a follow-up of the co-GNN that I mentioned, which is the second work, the authors also came up with an improvement of their own for the n-party setting, where they optimized for the number of rounds, communication and computation, where in general the idea was, rather than relying on a two-party protocol, they moved to a three-party protocol. So the threshold, I mean, they obviously achieve better efficiency, because now the computation complexity associated with the two party is not there. You can have efficient protocols in the three party setting, which allowed them to improve their solution. But the collusion threshold still remained 1, which is very, very bad. So, yeah. Okay. So this, I think, gives us a big picture about all the works that have been there, all the works that have looked at designing generic frameworks for secure graph computation. So the objective for the rest of the talk will be to highlight some of the key ideas so although there have been multiple works, there is one common thread that stitches all of these together. So the idea will be to discuss that the common theme across all of these. Okay, so the first work that was proposed in this direction was GraphSC, as I already mentioned. The idea here was, as I said, to represent the graph using what is known as a list-based representation, and in fact, it's called a data-augmented list-based representation of the graph. So, for example, if you have a 3-node graph and with 5 edges, you essentially store a list wherein you have one entry corresponding to every node and every edge in the graph. Okay, so you have an entry corresponding to V1, V2, V3, since it's a 3-node graph, and you have an edge corresponding to, so the edge E12 is basically denoting an edge that starts from vertex 1 and terminates at vertex 2, right? So you have, so the underlying assumption here is that you can operate on directed graphs as well. In fact, most of the frameworks assume that the underlying graph is directed. So in case you're operating on an undirected graph, then you assume that edges are there in both directions. Okay. So we'll operate on a directed graph, and this list essentially has an entry for every node and every edge in the graph. So it's every entry has some attributes or data associated with it. So, for example, okay, another thing to note here is that we are going to process the graph by looking at the list representation of the graph, right? So, and you have entries corresponding to nodes and edges. So, since you want to design a secure protocol, the underlying representation should be such that you should not be able to distinguish between an entry that corresponds to a node and an entry that corresponds to an edge. So what we essentially have is a common set of attributes that is maintained for every entry. So every entry in the list has the following set of attributes. So you have a source, which is SRC, you have a destination, DST, and you have an attribute called isVertex or isV, and you also have some buffer to store the data component associated with every entry, right? So whenever you're dealing with a vertex, there is no notion of a source or a destination. It's the source and destination attributes are usually used to denote information with respect to an edge. So whenever you have vertices, the source and the destination would just be the node number itself. And the is vertex is basically like a flag that is used to denote whether the entry that you are currently operating on is a vertex or if it is an edge, right? And the data component is some attribute that is associated with the vertex. So very similarly, you have attributes associated with an edge as well. So in case of an edge, of course, it makes sense to have information with respect to source and destination, because for an edge, the source attribute denotes which is the source node, and the destination attribute denotes what is the source, what is the destination node to which the vertex, which the edge points to. And as you would have already guessed, is vertex is denoted or is flagged to be 0 to denote or capture the fact that it is an entry corresponding to an edge. And every edge could also have some data component associated with it. So this in general captures, in fact, across most of the frameworks, I think they stick to some version of this representation. The length of the list would leak the total number of edges plus vertices. So V plus E is assumed to be public. There can be ways in which you can avoid it. So as I said, total number of nodes is never, it doesn't make sense to hide the total number of nodes, because multiple parties should have some mechanism to denote what an edge is. But total number of edges can still be hidden by using some amount of padding. If you, for example, the simplest solution that I can think of is if you have an upper bound on the total number of edges that any vertex in your underlying graph has, then you can pad with n, whatever is the residue remaining for n times. If n is the number of nodes and d is the maximum degree, then you know that the total list size would be n plus nd. So you would pad with whatever is remaining with dummy entries. But usually, in most of the works, they leak the total number of edges. So some leak only the total number of vertices plus edges, but some leak the total number of vertices and which means since you know the total list and the total number of vertices, which means you know the total number of edges anyway. So yeah. Yeah. You could, degree can be sensitive. So some applications may say that we don't want to leak the upper bound on the degree, in which case you're better off having a list of this sort, because you don't know how many vertices have what sort of, what is the degree of every node. And again, just recalling, it is whether an edge is present between node 1 and node 2 is what we ideally want to hide. We don't want to show whether two nodes are connected or not. So the total number of nodes and what are the nodes in the graph is usually public. Where there is an edge and what are the attributes associated with the nodes and edges, what we wish to hide. Okay. So, okay, that's, huh? Okay, that's a good question. So let's say we are dealing with a directed graph. So we can make the assumption that if I am a party, so, okay, let me, yes. So for example, bank A is one of the parties. So bank A is going to be responsible for distributing or secret sharing or giving the information with respect to all the nodes that it houses. So whether an edge is present between the nodes or not is something that it should decide. It's the private input of that party. So that party can misbehave, which means it is as good as an incorrect input being submitted by the bank, right? But a good question would be, what if there is an edge between a node within my view and a node that is held by another party, right? In which case, for example, the simplest solution would be if you're assuming a directed graph every node or every party that is responsible for that node would be responsible for secret sharing the edge that corresponds to an outgoing edge. So you can ensure that every party sort of is responsible for only the outgoing edges. So that way every party can choose to report an edge or not. But you could have mechanisms in place. For example, if you have two parties, so for example, this edge between these two nodes, which is an edge between a node that belongs to bank A and a node that belongs to bank B, we could have mechanisms wherein every edge that is reported by bank A across such things should be committed by both the parties. Okay, but that makes things a little more complex. So we'll assume the simplest scenario, where we assume that every party is responsible for giving information, or this edge, if it is an outgoing edge, is going to be a part of the input of bank A. So every party is responsible for distributing the data with respect to all of its own nodes, its own edges, and all of its outgoing edges. I mean, this is just for convenience. You could define it the other way around as well, depending on whatever is your application scenario. Okay.
So it's not be that expensive to check the verify the edges which are between two entities. That is added correctly.
I mean,
You have to think about it, but
no, I mean the safest bet is to actually commit to the adjacency matrix, where every entry could have both the parties committing to the same value there, and then translate it from the adjacency matrix to a list. Because otherwise, how do you obliviously commit to every edge or not? Yeah. Okay.
that will still be a one-time.
Yeah, it will still be a one-time pre-processing cost, and then so just to repeat a question, how would you, I mean, how expensive would it be to ensure that both the set of parties who have the associated edge to commit to it? So essentially, if you want to do this data obliviously, the thing that's coming to my head is you ensure that both the parties commit to the adjacency matrix. So every entry would correspond to two parties who will hold that entry. So you ensure that both the parties commit to whatever, either a 0 or a 1. And once you have the adjacency matrix, you extract out only the valid entries in the adjacency matrix to get back the list-based representation.
So your graph always becomes static.
Yes, yes. So there are some, of course, as a part of the second talk, you'll see that there are frameworks that are being designed for dynamic graphs as well. But for this part of the talk, I'm assuming that the graph is static. Okay. All right. So given the representation of the graph, what GraphSC essentially facilitates is to evaluate any graph algorithm, as I said, that can be expressed as what is known as a message passing graph algorithm. The idea of a message passing graph algorithm is as follows. So you have multiple iterations of performing some sequence of operations which is known as scatter, gather, and apply. So in each iteration, each iteration consists of, each iteration consists of repeatedly or sequentially applying these operations of scatter, gather, and apply, wherein the idea of scatter is that every node which has some information or some attributes stored with it, it will send out this information across its outgoing edges, which means it's going to scatter this information across all of its outgoing edges. And once the scatter operation is performed, what is done is gather, wherein every node now, so every edge now houses all the information that it has received from the nodes. And as a part of gather, every node gathers information across all of its incoming edges. So this again is just I mean, you can change the direction in which scatter and gather can happen depending on whatever is the graph algorithm. But just for convenience, we're sticking to the notion of information is scattered across the outgoing edges and it's gathered across the incoming edges. right? So once you perform the scatter and gather, you have the third state, which or third primitive, which is known as the apply primitive, wherein all the information that is gathered is used to update the state of your node, right? So most of your graph algorithms like BFS, DFS, PageRank, all of these can be expressed as message passing algorithm, which means you break them down into a sequence of performing some scatter, gather, apply, and this is done across multiple iterations. So in every iteration, there is a state that is maintained with respect to every node, and there is a state that is maintained with respect to every edge, and it keeps getting updated across multiple iterations. Okay. So just to give you an example, let's say we start off with having a 3-node graph, the same graph that we had, and let's say we are interested in looking at the reachability problem, which is we want to identify all those nodes that are reachable from a given node, right? So I start off with all the edges having no information, and only the nodes have attribute which is either a 1 or a 0. So the source node from where I want to actually check for reachability has the attribute 1, all other nodes have 0. So as a part of scatter, what would every node do? It would scatter its information across its outgoing edges. So vertex V1 would send 1 to 0, vertex V2, and vertex V1 would send a 1 to vertex V3. Similarly, each of the nodes V3 and V2 would send 0 across all of its outgoing edges. This is what constitutes a scatter. What would happen as a gather is every node now looks at what are all the data items that are present across its incoming edges. So V1 has just one incoming edge, so it just updates its or captures this information that 0 was what was propagated, and what vertex V3, since it has 2 incoming edges, it captures both the pieces of information that was scattered on it. So this is what happens as a part of gather. Gather, as the name suggests, it just gathers all the information that was sent across all the edges. And the apply function or the apply primitive essentially looks at updating the current state of the vertex based on whatever was the information that it gathered. So every vertex, as you can see, so the simple apply function that I'm doing here is I'm updating my state as long as there is at least one present in it, right? So vertex V3 also sees a flag of 1, and vertex V2 also sees a flag of 1. The moment I see at least one flag, if I'm flagged at least once, then I update my state to be 1. So just a single iteration of scatter gather apply allowed me to identify all those nodes that are reachable from the starting source node. So you run this across multiple iterations is what will allow you to get reachability from the source node. So for example, yes. So if one iteration would be one distance away, I run this for k iterations, then I identify all those nodes that are reachable from a k hop, right? Yeah, I hope this example gives you an idea of what scatter, gather, apply paradigm sort of looks like, and what exactly is a message passing algorithm. Okay. So as I said, the GraphSC framework essentially looks at how do you securely evaluate any graph algorithm given this representation, or a data augmented or a DAG list representation of the graph. And what you want to do is securely facilitate scatter, gather, and apply, right? So we want to do this in a data oblivious manner, which means the operation should be independent of whether you're looking at a edge entry or whether you're looking at a vertex entry. So in order to perform scatter efficiently, you want the list to be ordered in a specific manner. So because scatter is all about propagating information from a vertex to all of its outgoing edges, in order to perform scatter efficiently, we want to represent or reorder the entries in the DAG list in the following manner. So every node should precede its outgoing edges. So you have vertex V1 followed by all of its outgoing edges, followed by vertex V2 and its outgoing edges, followed by vertex V3 and all of its outgoing edges. So you have all the nodes also. There's a sequence, or you assume there's a numbering to the nodes, and you want all the nodes to appear in the same order. and in between all the nodes you want the set of edges, outgoing edges, to be present. Similarly, because your gather is about gathering information from your incoming edges, so the entries in the DAG list, so it's the same DAG list that is just reordered to facilitate performing scatter and gather efficiently. So in order to perform gather, you would want all the incoming edges present before the corresponding vertex. So again, you want all the vertices to appear in the same sequence, but then all of its incoming edges should precede the entry corresponding to the underlying vertex. Okay. Hoping that the underlying representation of the graph and the different orderings that are required to perform scatter gather is clear, we'll take a look at how exactly scatter is done. Okay. So as I said, scatter is about taking information from a given node and scattering it or propagating it to its outgoing edges. So just for convenience, I've sort of split out the data component across all these entries. Please note that there is just a single list, just so that it becomes easy to visualize. What I have extracted out is the data component associated with every entry. So as I said earlier, you shouldn't be able to distinguish whether you're operating on an entry that corresponds to an edge or you're operating on an entry that corresponds to a vertex. So there will be a data entry associated with an edge part of the entry and a vertex part of the entry as well. So if it is a vertex, the data component with respect to an edge will be 0. And if it is a vertex, then the data component with respect to the vertex will have some value and the data component for edges for V part will be 0. I hope that's clear, right? Okay. So it's just a single list that has all these attributes. I've just extracted them out as separate lists so that it's convenient to see what is happening. So how do we perform scatter? So we assume that the list is already sorted, or the entries are ordered. I should ideally say the entries are ordered in the source order manner, which means the source node appears before all of its outgoing edges. So what we essentially do is we perform, the naive approach is to sort of do a linear scan of every entry in this list. And as you are operating, or as you're performing a linear scan of the entries in this list, you determine whether you are at a vertex entry or whether you are at an edge entry, right? Let's not worry about how to do this data obliviously, but what would the naive approach look like? So every time you are at a vertex entry, you pick up whatever is the data item associated with it. And because you're doing a linear scan, you keep dropping the data item and updating the state of the edges. And you repeatedly do this whenever you encounter a vertex. So you pick up at a vertex, drop it at edges, and again update whatever is the data item. You pick up the new item whenever you're at a vertex, and you keep dropping it wherever you encounter an edge. Right? So you perform a linear scan starting from the starting entry till the end, which will allow you to update the entries along the edge of the list, right? So for example, the edge could have already some data item associated with it, which is, let's say, y12. So the edge data is updated as a part of scatter by looking at, or by computing some function of both y1 and whatever was picked up, which is x1, right? So the idea is to pick up at every node and keep on dropping at every edge, and you pick up, the moment you encounter a new node, you pick up the new item that needs to be dropped, right? That's the high level idea of how scatter is done. If you think about how to do this data obliviously, it's very, very easy. There's a typo in this slide. So the data item that is picked is going to remain the same as long as if you're at a entry that corresponds to an edge, then your is vertex is a flag that is 0. So which means your data component just remains the same. Whenever you are at a vertex, your is vertex flag is 1, which means you update the data item to be picked. So this should be this should have been swapped. So you remove whatever was the previous value and update the current data value of the item. So assuming that you can do additions and multiplication securely in MPC, this is just straightforward, right? And similarly, the edge data can be updated as whatever is the data that's picked up, whatever is the function that you want to compute as a part of the data that's picked up, into 1 minus is vertex, which means if you're at a vertex, your is vertex flag is 1, which means no update happens. This update happens only whenever you're at an entry that corresponds to an edge. So a simple, naive linear scan from the start till the end by using the different attributes that are stored as a part of the adjacent edge list representation allows you to securely update the entries corresponding to the edges as a part of scatter. A similar idea is followed even in gather. So you assume that your DAG list representation is ordered now based on destination order, which means all the incoming edges appear before the vertex. So again, you do a linear scan of the entries, and this time you do the opposite. Wherever you are at an edge, you keep picking up information, and the moment you encounter a vertex, you drop all the items that you have picked up so far. Okay, the idea is very, very similar. Okay. The last primitive is basically apply, wherein I said that the idea is you've scattered information across edges, and as a part of gather, you have gathered information as well. Apply primitive is about updating the current state of the vertices based on all that you've gathered so far. So unlike the previous two wherein you had to do a linear scan, here a linear scan isn't really required because you can parallelly operate on every entry in the list-based representation, because each entry now already houses whatever is the information that's required to make the update. So there's no linear scan as such that's required. So this can be done very efficiently. So in general, how would a message passing round look like? So you have the list-based representation. You sort the entries so that you obtain a source order, and then you perform a scatter. Once you perform a scatter, you again rely on a oblivious sort to reorder the entries so that you get a destination order. Once you are at the destination order, you perform the gather, and apply doesn't really matter what ordering you have. So you can in fact, there are frameworks that combine these two, gather and apply phase as well. Sorting can be done in the pre-processing as well, but I mean, there are different ways in which you can transition between these two. So I think I'll come to that. Okay. All right. So essentially, every round in your message passing algorithm involves fixing on particular orderings, or coming up with reordering the nodes as reordering the entries in the list as required for scatter and gather, and transitioning between these different orderings when you're performing the computations. So when you talk about GraphSC, all this is done in a data oblivious manner, which means the data is secret shared, or specifically for the GraphSC framework, they rely on a garbled circuit based approach, as I said earlier. But the generic framework can be still applied for secret sharing based approaches as well, wherein you assume that the list is all secret shared and you rely on a data oblivious sort to reorder the entries as required for source ordering, and you perform scatter followed by transitioning into a destination order, perform your gather, and you keep toggling between these two different orderings of the underlying list based representation of the graph. Okay. So an improvement that was suggested, so this theme of securely realizing graph algorithms via this scatter, gather, apply remains common. Slight modifications to the same is what is done. I mean, there are optimizations that are proposed, but this is the general theme that is common across all these frameworks. So one of the improvements that was suggested by Araki et al. Was that if you rely on a GC based approach, it requires a lot of, although you save on rounds, you invest on communication and computation costs. But then moving to a secret sharing based approach means you're now going to pay the price of the additional rounds that's required for the interactive protocol among the multiple set of parties. So just to recap, what a secret sharing based MPC protocol looks like. So whatever is the graph algorithm, you represent the function as a circuit, and the parties secret share the inputs to one another, and the entire circuit is evaluated gate by gate while maintaining the invariant that the inputs and the outputs are always secret shared. And interactions are required whenever you have like a multiplication protocol, etc. And linear operations are of course free. So essentially you assume that you have a circuit that represents the underlying graph algorithm and you securely evaluate it. The observation that the follow-up work by Araki et al. Made was that you would require to obliviously sort every single time you want to toggle between the two representations. What they observed was that you don't really need to rely on a sort, because a secure sort to transition between the source order and destination order would require log of v plus e number of rounds. But instead we can improve this by, I mean, you can have just constant number of rounds by relying on what is known as the shuffle and then sort paradigm. The idea here is that
Why is it order of log plus b plus e rounds?
because I think it's in the outsource setting, but it's essentially running any oblivious sorting algorithm, which would have depth of log v plus e, right?
Yeah.
In the secure sort. Yes. So, which is why it's the rounds which is log of v plus e. But what was observed was you can in fact rely on a shuffle and then sort paradigm, which will give you constant number of rounds. Yeah. So, but even in this case, the idea is for you to be able to do, I don't think I'll get into the details of what exactly is the shuffle and sort paradigm, but the idea is, okay, the idea is that, okay, you start off with a random ordering of the underlying list space representation, and you perform secure sort once. And because you're toggling between the same set of orderings, you can actually fix on the permutation that is required to move between these orderings. So you don't really have to do an oblivious sort every single time, but once you've done an oblivious sort, starting from a random ordering of the list, you can rely on publicly keeping that permutation that takes you between these two orderings, so that you have a constant number of rounds every time you toggle between the two orderings of source order and destination order. This is okay. This was one of the improvements that they suggested in order to improve the round complexity when you transition between the different orderings. But they also proposed a round optimized variant for improving how scatter and gather can also be performed. Okay. So in general, the idea is rather than performing a linear scan, you can essentially look at multiple entries at the same time to achieve better round complexity. So you basically parallelize the operations by looking at multiple entries. I won't go into the details of that. So even the round optimized variant for scatter and gather, to perform scatter and gather, was also already proposed, which required log of v times f, where f is essentially whatever is the computation cost for performing individual operations as a part of scatter or gather. So as a part of scatter and gather, I said you will have some function f that you will compute to update whatever is the state of your node and edges. So if your individual operation or that function requires O of f time, then you additionally have a log v overhead associated with it. Okay. So what will follow as a part of the next talk is one of our works, which is called Graffiti. So we continue to operate on the list-based representation, and we continue to hold all the improvements that was suggested by Araki et al. What we observed was that you can in fact improve the way in which scatter and gather can be performed. So that's what we'll get into in the next part of the talk. But just to leave you with The general framework that was suggested by GraphSC is what everybody, all the generic frameworks sort of optimize on top of. So, in general, the asymptotic complexity of the GraphSC framework is as follows. So, if you assume just if you look at the round complexity or the communication complexity, the linear variant wherein you are assuming that you are linearly scanning the entire entries in the list-based representation would require linear number of rounds in terms of the number of nodes and edges that are present. But with the improvement of secure shuffle, transition between these different orderings is now a constant number of.
Assuming constant number of parties.
Yes, in the small party setting, yes. Yeah. Yeah, and I'll let you sink that in. And that's it. So we can have, we can address any of the questions that can come up as a part of the second part as well, because it's very linked. So maybe we can, otherwise if there are any questions, I'm happy to address them. Oh, it's the round optimized variant.
I had a question. So the operations that we're performing were happening on the global graph, right?
Yes.
So how do parties communicate and get to this representation in the first place?
So there are multiple ways in which this can be done. So the simplest way is, let's say you do a one-time. It depends on what are you allowed to leak. So, for example, if every party is okay leaking the information of how many edges are associated with it, so it's not going to leak what are the edges, but if you're okay with every party leaking, let's say, how many edges are there, then every party can just secret share the set of entries that correspond to its nodes and its edges. So you just concatenate all the entries across all the parties, which will give you the list. But let's say you are not interested in leaking what are the total number of edges, then what you essentially have is all the parties will run a protocol to sort of populate the adjacency matrix. So they'll secret share entries corresponding to, so if I am a party and I am responsible for, let's say, node 1, I will be responsible for secret sharing all the entries corresponding to the first row, right? And which means I'll secret share, all the parties will collectively secret share the entire adjacency matrix, and then you basically do a sort, let's say, to identify only all the valid entries. Yeah. Thank you. Okay, thanks.
No, I have a couple of questions.
Oh.
So you mentioned that you have you're sticking to generic graph algorithms.
Generic frameworks.
Yeah,
Yes.
generic frameworks. But this scatter, gather, and apply this
Mhm.
paradigm.
Mm-hmm.
This captures all kind of graph algorithms, or what does the cost paper say? Does it say anything about it?
They don't really give like a statement like all graph algorithms can be expressed as message passing, but most of the graph algorithms that we operate on can be given as message passing.
Okay, so did you really think, are there algorithms which cannot be represented by?
That was one of the questions that we kept
It's
pondering.
not about efficiency, I'm actually talking about feasibility question. Like, can any graph algorithm be represented as?
I don't think we have come across any graph algorithm that cannot be expressed as message passing, have we?
I think for every graph algorithm, at least there were some parts.
Some parts that
which
can be done, yeah.
done.
Some part, there are some part which cannot be.
So, for example, are you thinking of GNNs? Cycle detection, I think, can be expressed.
What this scatter gather on a high level captures is like computations of the form A times X, like
Yeah.
f of A times X,
Yes.
where A is like the adjacency matrix
X is a vector that captures the data that's associated with all the nodes.
That captures all the data.
So you're essentially doing A times X. But rather than operating on matrices, you do this via lists so that you just operate on the list. But they're essentially operations of the form A times X.
So then
So-
all graph algorithms theoretically, feasible.
I think all graph can be done, but in this kind of scenario, we believe every vertex have to say from the next round.
Yes.
But some graph algorithms, they are not always all vertex need to say something. So let's say one vertex
Without
is
loss
active.
of generality.
Which means as long as even there is one vertex that is sending,
Yeah, like
you
others
can
should be
run.
idle kind of.
That can be simulated. I mean, you can have a protocol where only one party actually communicates and the others just send dummies. So,
Ideally, I guess we can do, but complexity.
feasibility I think is,
Question.
yeah.
I mean, whether you get the best, secure graph computation.
Any
from
computation
this
you can
or
do,
not.
like each time, each vertex and each edge will compute something. Here, all kind of this page rank and all those kind of algorithms, we are updating the state each round.
Right.
Each vertex is updating, but those states might be not just only one vertex is updating and it passed something, so
Yeah,
next is
exactly. So
updating.
efficiency is a different question.
Yeah.
That's what I'm saying. Yeah.
Feasibility wise, I think, yeah, it should be
Agree with me, Bhavesh?
the case.
Like we can do any graph, I think.
Yeah.
Any graph.
I mean, for all practical reasons, I think yes.
Algorithms,
I cannot give it.
Huh.
all like normal algorithm class, whichever algorithm taught
Yeah,
us.
there's no formal proof that says that every graph algorithm can be expressed as a message passing algorithm. I don't think that's there. But I think the general belief is that most of the popular graph algorithms can be expressed.
And you said that you have not mentioned some of the specific graph algorithms. Are
Right.
they related to that page rank?
Yes, there are some works that our own works that have looked at using these generic frameworks, but optimizing it for the underlying algorithms. Like, for example, I think we've looked at computing local cluster. So you're given the clustering algorithm. So you could have optimized protocols for the specific application. So that's also something that people have looked at. But for this talk, I think we stuck to generic frameworks that allow evaluating any graph algorithm. Yeah.
We say that the graph algorithms which are dependent on just the neighboring nodes,
Mhm.
like all those algorithms can be done by this message passing. Like whichever, like you told BFA shortest path, they all are dependent on like only the adjacent nodes.
But for example, if you talk about community detection, right, you want to identify a community in a social network. It's not just dependent on my immediate neighbor. It could be information. Of course, you by definition a community is all those vertices that have dense edges within the community and sparse edges across. So there is this reachability that is
But
still
that,
there.
that
But
message eventually come to you.
yes,
So
which is why it boils down to reachability is still there, but it's not. I mean, I wouldn't say it is just my neighbor. Thank you.
going to take the second half of the secure graph computation, and after that there is
Q&A and lunch.
Q&A and lunch. Of course we have lunch. Yeah, so I think we have kept some cushion time for discussing and like really active discussion, not just you sitting there. So try to get as much as possible, and we will try to decide on some open questions which can be taken beyond the workshop as well. We can start talking about the ideas. Anyway, the stage is yours.
Okay, so hello everyone, I'm Bhavish and I'll be continuing the talk on secure graph computation. So in the first half of the talk, we saw what the problem statement was, what different settings in which this problem was considered, and also we briefly saw one of the works, which was GraphSC, and how they did secure graph computation using the list-based representation, right? And GraphSC is something that, again, that is tailored to this outsourced computation setting. So we'll first see, in this particular talk, we'll first see what are the bottlenecks that are there in GraphSC work that was discussed in the first part, and how you can improve, how we improve that, and propose a new framework called Graffiti for the outsourced computation setting. And then we'll also touch upon the non-outsourced computation setting, and what are the bottlenecks of existing works in the non-outsourced computation setting, and how we improve upon them. And finally, I'll end with some new works that are there in this area, as well as some open problems. Okay, let's get started. So first, in the outsourced computation setting, just to give a high-level idea, what happens is that you have multiple parties, say banks over here. They would secret share the list-based representation of the graph among these three outsourced servers, or some small number of outsourced servers. And these servers would run an MPC protocol to compute on this secret shared list-based representation of the graph. Basically, they'll be doing scatter, gather, and apply based on, let's say, the algorithm of GraphSC. And finally, they would return the result, reconstruct the result towards these parties, right? So this was, on a high level, what was happening in GraphSC. You had a scatter, which happened in the source order, where you require a linear scan, followed by a transition to destination order, where you did gather and apply, and back to source order for the next iteration of message passing, right? And this was the complexity, theoretical complexity. So in the linear variant, where you're doing a linear scan on the source order for your scatter, you'll incur a round complexity that is order of v plus e. And communication would also be order of v plus e, because at every entry you're doing a multiplication, which would require order of 1 communication. And secure shuffle is what we use to do a transition. So given a one-time sort, where you generate sharings of the permutation between source order and destination order, in the subsequent iterations, what you could do is you could just apply this permutation using a primitive known as secure shuffle, and this would require only order of 1 rounds. Again, order of 1 in the non-outsourced setting or in the small party setting, and communication would be order of v plus e, which is the size of your list that you're operating on. And finally, similarly, you have destination order, where you will do gather. In the linear variant, it would incur order of v plus e rounds and order of v plus e communication. Now the GraphSC, they also propose this round optimized variant. On a very high level, the idea is that instead of doing this linear scan, you can parallelize it, and you can do this scatter or gather in a tree-based fashion, right? You look at different segments in the graph and you operate them, and in the next iteration, you combine these two segments, the results of these two segments into one, and so on, right? And that's why this would reduce the round complexity from v plus e to log times v. But this comes at an increased communication cost, which is
log v plus e.
Right. So the it's log v because like v is the bound on the degree of every entry, right? So at every, you can have segments of at most size v only, and then you can start combining them. So that's why it's log v, right? Yeah. Okay, so this is a theoretical cost, but how does it translate when you're trying to practically realize some graph algorithm securely, right? So let us consider a simple setting where you have two outsourced servers, right? And then you want to do like one iteration of PageRank computation on a graph of size 10 power 7, right? If you take the if you consider, like, we'll measure the performance, the real world performance in terms of both the response time, which is the time it takes to do one iteration of PageRank computation, and also the communication. If you look at the linear variant, just to perform one iteration of PageRank computation, scatter requires 5000 seconds, right? And same as gather, and this is primarily because you're doing a linear scan. It has around, you need, like, the servers have to have order of v plus e, or 10 power 7 rounds of interaction, right? And if you just consider like a latency of 0.5 milliseconds, it still takes like 5000 seconds just for one iteration of PageRank computation, right? But you can see that the transition where you're doing using secure shuffle, it hardly takes any time, like compared to the time for scatter and gather. And similarly for apply as well. So for PageRank, apply would just be some multiplication operation, so which is why it doesn't take much time either, right? And in terms of communication, you can see that, okay, it's still not very bad, like 640 MB, which is anyway what you have to pay. It's coming due to the size of the list that you're operating on, right? But now if you consider the parallel variant or the round optimized variant, right, you can see that the runtime or the response time is certainly reduced. For scatter, the runtime is just 400 seconds as opposed to 5000 seconds in the linear variant. But it comes at a cost of very high communication, right? You have like you have to do 25 GB of communication just for scatter, which is pretty expensive, right? So the best would be like you have best of both, right? Like you have better you have better round complexity as well as like very low round complexity and very low communication as well, right? Which is what we will see how we can achieve that. And this was what our work was, and it's called Graffiti, right? So like GraphSC, this is also a generic framework to realize any message passing graph algorithm securely. And the key contribution was that we made the round complexity independent of the graph size. And we also concretely improved the communication and computation cost, right? And this came, and the way we achieved this is by actually giving a new and different realization of scatter and gather, which is what brings up to 3 orders of magnitude improvement in runtime, right? Okay. So like GraphSC, Graffiti also works on the same list-based representation, where every entry in the graph, every vertex and edge in the graph is a part of this list, and every entry is represented using the source, destination, is vertex, and data, right? So it should be represented like this, and for vertex, the source and destination is going to be the same, right? And like GraphSC, this also facilitates secure realization of message passing algorithm using scatter, gather, and apply. You already have seen an example of message passing algorithm. But unlike GraphSC, which relies on source ordering and destination ordering for efficiently realizing scatter and gather, in Graffiti, we introduce a new ordering called vertex ordering, where all vertices appear together followed by all edges. And also please note that the relative orderings of vertices and edges in all these 3 orderings will be same, in the sense that if V1, V2, V3 is the order in which the vertices appear in vertex order, in the source order also the vertices appear in the same order, right? This is required. Okay.
Do
Yeah.
the edges also follow source ordering?
Sorry?
In the vertex ordering, are the edges also source ordered?
Not necessary. That's not necessary. The relative ordering between the edges doesn't matter. What is important is that the relative ordering between the vertices should remain the same. That's all. Okay. Okay. So given the vertex order on a high level, scatter operation reduces to performing some non-interactive linear operation in the vertex order, followed by a transition to source order, right? So since the operations performed in both vertex order and source order are now non-interactive, as opposed to GraphSC where during the linear scan you are doing multiplications, over here this will not incur any cost. The only cost that will be incurred is during the transition between vertex order to source order, right? And which, based on the improvements of Araki et al., it can be done in like order of 1 rounds using a secure shuffle, right? Given one time you generate the mapping between these two ordering, you can do it using secure shuffle, which would incur on the order of 1 round. And similarly, gather would involve performing some non-interactive operation in the destination order, followed by a transition to vertex order, where again some non-interactive operations are performed. So again, only cost involved here would be the transition from destination order to vertex order, which given a one-time sort, you can do it using secure shuffle. Right. So I'll get into the details of how this works. But yeah, since you can see that all of these operations are incurring a round complexity that is independent of the graph size, your overall round complexity is also independent of the graph size. Right. Okay. So I'll explain how scatter would work in this particular paradigm. So just to recall, what you want to do is in scatter, the data that is present in the vertex should be scattered or propagated to the edge, outgoing edges of the vertex, right? And assume that now you're in the source order representation, where every vertex is followed by their outgoing edges, right? What you want to put is like, what you want to do is take this value x1 and put it in these edges, these first two edges. Take the value x2 and put it in this edge. Take the value x3 and put it in these two edges, right? But let us assume that what you're doing is, what you're going to do is basically that the data that is dropped off at an edge is going to be the sum of all the data values that are there in the previous entries, right? And this is just the, in the sense, like, ultimately what you're doing is just you're linearly scanning the list and then you're doing a prefix sum, right? So data dropped off at this edge would be sum of all the data entries, data values there in the previous entries. So it will be x1 plus x2 and so on. Now, if you observe over here, the first set of edges have the correct value propagated or scattered on them, whereas the subsequent edges have the correct value plus some error term that is being propagated, right? So the idea is that you, before doing this linear prefix sum over here, you correct for the data that has to be propagated by these vertex values, vertex entries, so that this prefix sum captures the correct data in the edges. And the way you do it is that what you observe is that the error in this particular edge is exactly equivalent to the data that is propagated in the previous edges, right? So we first order the list in the vertex order, where we update the data value of the vertex to be the current value minus the entry in the value in the previous entry, right? Once you have done this, you move to the source order, and now when you do this prefix sum, you can see that the correct value will be propagated, because whatever error was being generated from the previous vertex, it's being cancelled out by this vertex, right? And over here, if you observe, whatever we did in the vertex order was just a simple subtraction operation, which is non-interactive in secret sharing based MPC, as well as in the in the source order, whatever operation that we are doing is just a addition operation, which is also non-interactive in MPC. So the only cost that is incurred is for this transition between vertex order and source order. Right? I hope this is clear to everybody. Okay. So now let us look at gather. Gather also we have a similar idea for gather over here, but there is a limitation for gather, is that we need this aggregation operation. So in gather, what happens is a vertex is going to aggregate the data present in all of its incoming edges based on some aggregation operation. In GraphSC, this aggregation operation could be any operation that is commutative, but in our case, we need the aggregation operation to be a linear aggregation operation, right? And in case of a nonlinear aggregation operation, Graffiti, we fall back to the idea of GraphSC only, the parallel variant of GraphSC. But for linear aggregation, which by the way also captures a lot of real world, a large class of graph algorithms, uh, okay, this is how it would work. For simplicity, assume this aggregation operation to be a simple addition, right? And you're in the destination order. Assume that the value aggregated by a vertex is going to be the sum of all the values that are there in the previous entry, right? And again, this can be done by just doing a prefix sum, right? And if you do this, you can see that the first vertex has aggregated the correct data, correct value, but the subsequent vertices, they have aggregated the correct term is exactly the data that is aggregated in the previous entry. So what you do is, after doing this, you move to vertex order, right, where you can correct for this error, right, by just subtracting the data aggregated in the previous entry, right? And oh sorry, yeah, right, by subtracting the data aggregated in the previous entry. And again over here, if you observe, the operations that you do in the destination order as well as the vertex order are just additions and subtractions, so they're non-interactive with MPC. The only cost that is incurred is during this transition from destination to vertex order. Right. Okay. So just to give an overview, in Graffiti, one iteration of message passing involves transitions between vertex order, source order, and destination order. So we begin with scatter, which involves a transition from vertex order to source order, and then you have transition from source order to destination order, where you'll do gather, and gather requires you to transition from destination order to vertex order, and finally you have the apply operation, which does not require any specific ordering. It's similar to whatever was happening in GraphSC. Right. So now if you look at the, okay, yeah, I think one thing that we have not touched upon is how these transitions happen, right? I just said, okay, you generate this pairing of permutation that realizes this transition, and then you just have to apply it using secure shuffle. But let me get into the details of how that actually happens. Right, let us consider one particular transition where you want to go from vertex order to source order, right? Simple way is, yeah, you do a secure sort, but it will incur very high round complexity and communication complexity. But alternatively, what you could do is, you could first apply a random permutation on this vertex ordered list, right? Okay, sorry. Yeah, you apply a random permutation on this vertex ordered list, right? And you move to a random ordering of the graph, right? Now that you're in the random order, you can actually leak the mapping between this random order and the source order, right? Because this is just mapping source order to some random ordering of the graph, and hence it's not going to leak any topology, any information about the topology of the graph, right? But then you need to, again, at least once you need to do a secure sort, right? But after you do the secure sort, the mapping between this two ordering, that can be made public, right? So this would require like log v rounds in initialization at one time, followed by in the subsequent rounds, you'll apply this random permutation using a secure shuffle, followed by applying a public mapping. I hope this was clear to everybody. Okay. Okay, so now how does it translate to real life, real life performance for the same application of PageRank? So we are again considering a two-party setting with two outsourced servers, and let's say you're working on a graph of size 10 power 7 and you want to compute one iteration of PageRank, right? So if you look at it, Graffiti takes only 3 seconds for scatter, like almost like 3 to 4 seconds for scatter and gather, which is like tremendous improvement in comparison to both the linear variant and the round optimized variant. And even in terms of communication, you can see that it takes only 160 MB of communication, which is much smaller than both the linear variant and the round optimized variant, right? So overall, if you look at it, one iteration of PageRank computation on a graph of size 10 power 7, Graffiti can do it in less than 10 seconds, whereas linear variant and the round optimized variant take like a lot. Specifically, like there is 1,000 times improvement in comparison to the linear variant, and about 100 times improvement in comparison to the round optimized variant. Okay. And also when you we also benchmark graffiti for varying graph size, right? And you can observe that the runtime of graffiti, you can see that it's almost same even when the graph size increases. Like if you zoom in, there is a slight increase, but then it's almost the same. This shows that the round complexity, and this is primarily because the round complexity is independent of the graph size, right? Whereas for both the round optimized and linear variant, you can see that it's increasing with graph size. Right. Okay. So that was about the outsourced computation setting. Now let me move on to the non-outsourced computation setting. But if there are any questions at this point, I'm happy to answer. Yes.
So this is all for linear operations, right? So
Yes.
in practice, are there like graph algorithms that require non-linear operations?
Yes. So, for example, if you look at shortest path computation, um, that's one example where you need nonlinear aggregation. But in that case, the improvements of scatter is still there. Scatter would work for any graph algorithm. For gather, in that case, you'll have to rely on the approach of GraphSC. Although there is one follow-up work which actually reduced at least the communication cost. So if you remember, the round optimized variant had a round complexity of log v and a communication complexity of v plus e times log v. There's one work which they were not specifically looking at graph algorithms. They were looking at operating on a group list, but they propose some techniques which can be adopted, and you can reduce the communication to order of v plus e. Right, but the round complexity still would be log times v. That I think is unavoidable. Okay.
So,
Yeah.
just on this slide, right? If the graph is static, there will be just one possible sorting from vertex to source, right?
Right.
So why do we try to optimize this with the shuffle then followed by a sort?
Okay. So basically, you cannot reveal this mapping between vertex and source order in clear, and the reason is the following. Let me open a list. Right. Let me go to right. So let us say if I reveal the mapping between this vertex order and source order, that means I know that this entry is going to go and sit here, which ultimately leaks the degree of vertex v1. Right. So you cannot reveal the mapping between these two ordering in clear. So which is why you actually move to a random ordering by applying some random permutation, right? And then you reveal the mapping between those random order and this. Right? And over here, although I say shuffle, like in the subsequent iteration, you will be applying the same random permutation. So which is why you'll be moving to the same random order followed by applying the public mapping.
So this needs to be done just once.
Once, yeah. Okay. Any other questions?
Sort is done once, but every time you transition, you still have to do a shuffle.
Shuffle, that has to be done.
You pay the cost of shuffle, which is much lesser than sort.
But you would have to arrive at the same random order to be able to use this option.
Yeah.
How do you ensure that we always arrive at the same one?
I think parties would use the same randomness they used in the first instance. Right? So the way random shuffle would work is that every party would choose a random permutation, and the composition of that permutation is your ultimate random permutation. So in the subsequent iteration also, they'll choose the same random permutation they chose earlier.
But you still need to do the shuffle every single time.
Yeah, you have to do the shuffle every single time.
Similarly, in your GraphSC, you would have to actually do oblivious sort every single time. It's not just sort once.
Yeah.
Because if you recall, there's a data entry that's associated with the list. With every, I mean, there's a data attribute
Component.
associated with every entry. So that data
Keeps
attribute
changing.
keeps changing every single time you operate on it. So it's not like you can sort just once. Because you would have reached some ordering, you would have updated the data entry. Now you have to go back to the previous ordering with the updated value. So you have to sort every single time.
So it was sorting, but the list is getting changed. I mean,
the same, but the
Data. Updated. And you need to rearrange these data, updated data components every time. Okay. Any other questions? Okay, then I'll go ahead. So, okay. As opposed to the outsourced computation setting, there are several applications and instances where the parties are not comfortable in hiring a small set of or outsourcing their data to external servers, right? And because it comes with some trust assumption that these three servers do not collude, right? In some applications, it's also challenging to find such three servers, right? And this is especially true for transaction data where banks are involved. They are not comfortable with moving data outside of their organization. Right? So in such scenarios, you want to have a non-outsourced computation setting where the banks or the parties themselves participate in the protocol. Now this comes at a cost because in an outsourced computation setting, you can fix on the number of outsourced server beforehand, and you can optimize the MPC protocols for that particular setting. Right? You can have custom protocols for that setting, which means you can have more efficient protocols there. Whereas in this case, you don't know the number of parties beforehand. You have to rely on the general purpose MPC, and you'll have to rely on generic primitives that are designed for this general purpose MPC, and that would come at some some additional overheads. Specifically, if you take Graffiti, or GraphSC, let's say, and then you, since they are oblivious to the underlying MPC, you can instantiate them using a general purpose N-party MPC protocol, but then they do not perform well in such setting. Specifically, let's consider a simple setting where you have some N parties, right? In this case, you have, let's say, 15 parties, and you want to do 10 iterations of PageRank computation on a graph of size 10 power 5, right? Previously, in the outsource setting, we saw the results for a graph of size 10 power 7, but this is for a much smaller graph of size 10 power 5, but you have 15 parties, right? The runtime of Graffiti is as follows. Okay, sorry. This is for the initialization, which is the one-time sort that you do, and this is the cost for 10 iterations of PageRank after this one-time initialization of the sorting that you do, right? You can see that the initialization phase itself is very expensive over here. In fact, it ends up taking 80% of the total time, right? And this is because secure sorting operation is in general more expensive. And when you move to a general purpose MPC, it has round complexity that is dependent on both the number of parties, the linear in the number of parties, as well as logarithmic in the graph size, right? Which brings in additional overhead. And also, if you look at this message passing, this is also not very efficient, right? It takes 90 seconds for 10 iterations, so approximately 9 seconds for one iteration. But if you see in earlier case, for a graph of size 10 power 7, it took 9 seconds. And over here, even for 10 power 5, it's taking 9 seconds, right? And this is because even the message passing is not very scalable, because your secure shuffle protocol has the generic N-party shuffle protocols. They have a round complexity that is linearly dependent on the number of parties. Because as I said a while back, the way you apply random permutation is that every party chooses a random permutation, and the composition of all this permutation is your final random permutation, right? So each of this random permutation is sequentially applied, and which is why you have this dependence, linear dependence on the number of parties, right? Okay. So towards addressing those things, these particular issues is where when we came up with this framework called GRASP, which was specifically tailored for the outsourced computation setting. Specifically, we designed a lightweight initialization phase where we actually get rid of this need for secure sorting, and we also make the round complexity for message passing independent of the number of parties. Right? It is already independent of the graph size from Graffiti. Right? We build on top of it, and we also make it independent of the number of parties. Right? And the idea here is that we observe that in the non-outsourced computation setting, since the parties themselves are participating in the protocol, they still have some local information about their part or their view of the graph, right? And we use this information to actually optimize the message passing computations, right? And the idea is as follows. Okay, but before I get into that, let me give you a comparison with other existing works, right? So if you remember from the first talk, there were first an HE-based work. I have not included the theoretical comparison, but trust me, it's not at all practical. They take more than a day to compute on a graph of size 10 power 5 for few iterations of PageRank. So which is I have not included it over here. But then you have graffiti, which when instantiated in the n-party setting, it would have a round complexity that is linear in the number of parties as well as the graph size, right? This part is coming from the initialization, and this part is coming from the initialization where you do the sorting, and this part is coming from the message passing computation, right? So over here I'm considering you're doing k iterations of PageRank computation, right? In contrast, there was this work called Ring SG, right, which was proposed by Zhou et al. They come up with an idea where you can distribute this computations, they sort of reduce these computations to pairwise computation between parties, and which is why they are actually able to get rid of this order of n factor in communication, as well as the dependence of graph size and the number of parties in the round complexity as well. But this comes at the cost of a low corruption threshold. So you have some question?
Low means really low.
Yeah, really low. I don't think this is very practical, especially since you're in the non-outsource setting, right? Like if you think banks are there, right? It's possible that some banks are colluding, or it's also possible that one bank is acquiring another bank, right? Acquiring another organization. In that case, it will get to know all the data in that bank. So it's not a very practical threat model. But this is what they pay to actually achieve a communication complexity that is independent of the graph size.
Also imply in the outsource setting?
No.
Theirs is only.
In the non-outsourcing. They also leverage this information that every party has some information about their local view of the graph.
I think they mention about reputation. What is the
Oh, what is the justification they give?
rationale?
The justification they give is that if a bank is colluding with other bank, it would mean its data would also get exposed to that other party, which is what which is why they would not do. But I don't think that's a very valid argument.
So just
Yeah.
to clarify, this corruption only applies to that particular instance of the two parties, right? Amongst that pair, right?
So what happens is they sort of reduce this computation to two-party computation in the sense that let's say I as a party would secret share some information about my part of the graph between those two parties, so they could compute everything respect to their vertices, right? So I'll sort of secret share my edge data to those two parties, so for all the vertices that those parties hold, they can do this aggregation, right? So on a very high level, that's the idea, and this is where this threat collusion. So if these two parties are colluding, they could see my edge data,
I see. So
right?
it does affect parties outside the pair as well.
Yeah, exactly. It affects the parties outside the pairs. That's why it's okay. Yeah. In contrast, if you look at grasp, right, you can see it has a round complexity that is both independent of the number of parties as well as the graph size. But it has a slightly higher communication complexity of order of that is dependent on the number of parties in comparison to Ring SG. But I think that is required if you need to have stronger corruption threshold, right? But yeah, it has like the best features more. Okay, so I will now explain how we achieve this in GRASP. So in GRASP, what we propose is a new approach for realizing message passing computation, known as DCC approach, or decompose, compute and combine approach. And it's an oblivious approach for message passing that is designed to leverage local information known to the parties, right? So let us consider a simple graph distributed among three parties, right? Where each party has has two vertices in their view, right? Now, if you look at this particular vertex V6, right? Just a second. Can choose some. Is that particular? If you look at this particular vertex V6, right? For one iteration, just focus on one iteration of message passing, where every vertex should propagate their state and aggregate information from their incoming edges and update their state, right? If you look at the update for this particular vertex V6, it depends only on its immediate neighbors V2 and V4, right? So to update all the vertices belonging to party P3, let's say, it suffices to consider a graph consisting of only the immediate neighbors of the vertices belonging to P3. Does that make sense? Right? And the idea or the advantage in considering this smaller graph is that this particular graph is already in the view of party P3. In the sense that party P3 knows the topology of this graph. The party may not know the data values associated with, say, these vertices or these edges, but the party knows the topology of this graph, right? And that is what we leverage to optimize message passing computation, right? So the idea is that, okay, you first decompose this graph into subgraphs consisting of only the vertices and edges that are immediate neighbors of that party, right? So you will decompose the global graph itself into 3 subgraphs in this case, because there are 3 parties involved, where each party, where each subgraph consists of the local view of the particular party, right? So P1, this particular graph G1 consists of vertices belonging to party P1 and their immediate neighbors. This graph consists of vertices belonging to P2 and their immediate neighbors. And this again consists of vertices belonging to party P3 and their immediate neighbors.
Neighbors from where the edges are coming
Yeah.
to its
Yes. Okay.
Because you're aggregating or you're
Yeah.
gathering information based
Yes.
on incoming,
Yeah.
you're focusing on only
Right.
nodes that have incoming.
Yes.
But we can't do that.
Outgoing also it knows.
Sorry?
Outgoing also.
It knows outgoing also, but to update its current state, it only has to focus on its incoming edges. It doesn't have to worry about its outgoing edges.
Yeah, I have correct, but can we leverage that also somehow? I mean, you have not told me. Or
Leverage that for.
the view of that it knows the vertices, which will be impacted by its.
Right.
Can we leverage? No.
At least in this setting, I don't think we can leverage.
I mean, you have already thought.
Yeah. Over here, I don't think we can leverage it as such. But yeah. Okay. Yeah. So and then again, okay. So although we are decomposing it this way, we'll still be operating on the list representation of these subgraphs. I'll come exactly how you can do this decomposition, but we'll still be operating on this list representation of each of these subgraphs. That is going to be secret shared among all the parties, right? But then now they will be performing message passing computations on this list representation of these subgraphs or this decomposed graphs, right? And then you're going to perform one iterations of scatter, gather, apply on this list representation. And finally, you can combine this information. Basically, you take the updated state of vertex V1 and V2 from this particular graph G1, and then you take the updated state of V3, V4 from this particular graph, and then V5, V6 from this particular graph, and then you combine them, you get the updated state of vertices after one iteration, right? Now, a subtle thing to observe over here is just considering a vertex and their immediate neighbors is not is going to leak some information, right? It's going to leak some information about the number of neighbors this particular party has, right? That is not something that you want to leak. A naive approach that which I'll discuss is like you consider all the vertices, but only the necessary edges, right? That would hide this information, right? That's a naive way to do it. But then the disadvantage of doing that is that you're considering all the vertices for all the subgraph, which means you're processing additional vertices, which would come with some additional overhead in terms of communication, right? But we'll get into that, but this is a subtle thing that I want to mention. So now I'll explain how this decompose, compute and combine happens in MPC and where exactly the improvements come in. Right? So unlike graffiti or GraphSC, in our case the graph itself is represented in the form of a multiple data augmented list. Specifically, we have a vertex list V, and we also have an edge list corresponding to every party, where E1 consists of all the incoming edges terminating at vertices belonging to V1. Right? So E1 will have all vertices terminating at V1 and V2. Similarly, E2 will have all all edges terminating at V3 and V4, and E3 will have all edges terminating at V5 and V6. Right? Okay. So given this, your decompose step, so this is going to be secret shared among all the parties. Given this, your decompose step is going to be just generating the data augmented list representation like used in graffiti for all the decomposed subgraphs G1, G2, G3, right? And that step is very simple. You take the entire vertex list, concatenate it with E1. That is going to give you the first list representation of the first subgraph. And similarly for G2 and G3, right? And since this is just you're collecting some shares and concatenating, it's going to be a non-interactive operation, right? It's going to be it can be locally done by every party, right? And given this, at each of this subgraph, in parallel we are going to perform message passing computations, which would mean like you do scatter, gather, and apply, right? For now, I'm just considering this particular first subgraph G1, but you can consider all of them to occur in parallel, right? If you look at it, the message passing computation will follow the similar approach as graffiti, where we will do a transition from vertex order to source order to realize scatter, source order to destination order for to begin gather, and destination order to vertex order for gather, and finally apply, right? But then what we are improving is how these transitions are being realized. You can see whatever operation we do in vertex order, source order, destination order is just non-interactive operation. They do not give any overhead. It's just this transition would require a shuffle, and also to first generate a permutation between this transition, you need to do a sort, which was the overhead, which we can see that it can be eliminated here. And the idea is that, okay, just to recap, in graffiti, how do you do this transition is that you first do a random permutation from vertex order to some random order, followed by you do a secure sort once and reveal this mapping in clear, right? But over here, you know that this particular graph or this particular mapping between vertex order and source order for this decomposed subgraph G1, it is known to party 1, right? Because it's a graph that is in the view of party 1, right? Which means this mapping is already known to party P1. So this random permutation that you apply could just be a random permutation known to party P1, right? And this can be applied using a much more efficient primitive known as permute plus share, right? Which allows you to permute a list based on a permutation known to one party, right? And this has order of 1 rounds. And finally, this since this permutation is now known to party P1, P1 can simply generate this mapping between random order and source order locally, and then share this mapping to others. So you don't even have to do a sort once in the initialization step, right? So that's the main idea, where you can see now that you're at every iteration you're just going to use permute plus share instead of shuffle, where you're applying a permutation known to one party and followed by a public mapping given by that party.
So everybody will probably assume that this is already there with P1. So why is it even letting others know?
Letting others know what?
I mean
This public mapping.
yeah, the data is still distributed.
Oh, right. Yeah, the edge data and everything is distributed. So this graph anyway is like secret shared. This list is secret shared. Only thing is like this mapping is known to party P1. I was hoping that was clear to everybody. Or is it not? Okay. Yeah, so basically this graph in the decompose step, so the graph itself is represented like this. This entire list, all of these lists are secret shared, right? And during decompose, we just collect these shares. So every party would now have secret sharing of this list G1, G2, G3, so on. And they have to do message passing computations on the secret shared list, right? The data component is still secret shared. Right? Okay. Yeah. And what we are optimizing is basically how these transitions can be done, which ultimately also gets rid of the initialization step that was required in graffiti. Right? And finally, uh, and finally you have to.
This is also fixed, just like the case of shuffle.
So this random permutation can be fixed, and then this public mapping is made known once.
Only once.
Yeah. So in the subsequent iterations, you only have like, so the initialization phase basically involves, in this case, each party choosing a random permutation and computing this mapping and sending to others. The subsequent iteration, you just apply one iteration of permute plus share followed by a public mapping. Okay. And finally, combine is again just collecting shares of the corresponding vertices from different subgraphs and then combining them, and also just collecting the edge list, updated edge list after the iteration. Right? So this is how one iteration would look like. You'd first decompose into subgraphs, you'd parallelly compute on all the subgraphs and combine. In this particular version I mentioned, both decompose and combine was non-interactive, and compute involved 3 invocations of just permute plus share instead of shuffle, which has like order of 1 rounds or rounds independent of the number of parties. So the overall round complexity for one iteration of message passing here is going to be independent of the number of parties. Right. Okay. So now how does it translate to in terms of performance? Just a second. Yeah. So if you look at the same case where you have like 15 parties and you're computing 10 iterations of page rank computation on a graph of size 10 power 5. Graffiti required 661 seconds, whereas GRASP initialization, there's no sorting involved. It is just each party sampling a random permutation and sending a public mapping to others. So it hardly takes any time. And also message passing, you can see that we have up to 10 times improvement because we got rid of this linear dependence on the number of parties. Right? And again, in the initialization, in the communication side also, in the initialization, we save on the communication a lot. You can see the slightly higher communication cost in comparison to graffiti for the message passing, and that is precisely because at every subgraph you're processing some additional vertices as well, right, which is required to hide some information. You can further optimize that as well, but in the interest of time, I'm not going into the details of that. You can look at the paper for that. And also, again, we compare it, both graffiti and GRASP, for varying number of parties, right? And we observe, again, you can observe over here that the line is almost constant. And there is a slight increase if you zoom in, but it is not linearly increasing with the number of parties. Okay. Okay, I think I'm done with the non-outsource setting as well. If there are any questions I can take, otherwise I'll move into the future works. Sorry?
Secure sort.
Oh, so secure sort is, let's say you have a list of some values, right? You want to sort it. If you naively just sort it, you will leak which element is greater than or smaller than you'll leak the relative relation ordering between these, right? In a secure sort, you want to hide that. So that is what secure sort is.
So why is log of
Okay. Okay, yeah. Round complexity would be log of V, because you can think of it like, for example, quick sort, right? What you would do is you would choose a pivot, and then you would move all the elements lesser than the pivot to the left and greater than the pivot to the right, right? And then you need to do this log V many times, asymptotically at least, right? So over here in MPC, each of this time you're choosing this pivot and doing this comparison is going to require some interaction, right? And reordering. And then you have to do this order of log V many times. So that's why it's order of log V. Does that make sense?
So it is done for only single time.
In graffiti, you do it only for single time. Okay. If there are no questions, I'll move ahead. Yeah. So there are actually a lot of open questions in this area, I think. The first is that although there are many works, the most of the works have been limited to some specific type of graph or some specific threat model, right? And there are many things that are left unexplored. Right? Simple case is like most of these existing works consider only static graphs, right? Graffiti, GraphSC, Grasp. They do not talk about different types of graphs. They just consider a simple directed static graph, right? But there are also these multi-graphs where between two same vertex you can have different types of multiple edges, each corresponding to some different attribute, right? And you want to you want to compute some algorithm over that graph, right? In that case, there's this work called Multisend in PETS 25, which addresses this particular issue. Like they also work on top of Graffiti, but they optimize the algorithms for this multi-graph when you're considering multiple different types of edges between the same vertices, right? And second thing which is more interesting is that all of these works consider the graph to be static, right? But in a real world scenario, most of your graphs are dynamic. They're constantly evolving. There are some vertices being added, some edges removed, new edges added, etc. In that case, if you're operating over Graffiti, every time graph changes, you have to do this initialization, or you have to generate these mappings using sort again, which is very expensive, right?
What about Grasp?
In case of Grasp, you don't have to do that. But then again, if you look at it, every time the graph is updated, the party has to communicate some message to the other party that is of the size of the original graph, right? Because the mapping, it has to locally compute and communicate, right? So can we do something better? Ideally, what we would want is whenever a graph is being updated, you update this whatever state that you have with, say, communication that is dependent only on the size of the newly added entries or something like that, right? So there's one work that is like a joint work with Karthik Nayak and Ethan Chen from Duke University. This is not yet public, but it will soon be made public, where we look at how you can optimize Graffiti or GraphSC based works in the outsource setting for dynamic, and avoid the need for the secure sorting every time the graph gets updated, right? So look forward to it. And these are some works that like very recent, last year and this year. But then there are also other open problems which I think people have not looked at yet. One is different threat models. Most of the existing works, they look at only semi-honest setting, right? Even in our case, we just consider semi-honest setting. When you move to malicious setting, things become more challenging, right? For example, I think one thing that was discussed was in the previous talk was if there is an edge that is shared between two parties, right? Let's say in Grasp, when I'm just sharing all my incoming edges, I as a malicious party may choose to avoid that particular edge, right? So there should be some consistency check that has to be done to efficiently ensure that the graph is generated correctly, or the secret sharing representation of the graph is generated correctly.
Not just for the shared entries, but also about its own subgraph.
Yeah, exactly. In case of Grasp, since each party is responsible for, say, sharing this mappings for different orderings for its own subgraph, right? Even that malicious party can give incorrect values just to harm the computation, right? So over there also you need to have some additional consistency check, and you want to have these consistency check at a low cost. In the first half, when you discussed, we said, okay, one way is that you commit to this adjacency matrix and then you generate the list representation. But then if you have, like, say, 10 power 6 nodes, adjacency matrix doesn't make sense, right? So you have to do something better, which is challenging. And also there are other threat models like rational adversary or covert adversary. So it's interesting to see how you can extend these techniques there. And another interesting problem is like public verifiability. So oftentimes, let's say if you're doing some computation for anti-money laundering or, say, fraud detection, after this computation, the parties would like to report these whoever was flagged to some other higher authority, right? But this higher authority would need some proof or something that the computation was done correctly, right? So you need something known as publicly verified, where anybody could verify that, okay, whatever computation was done on this particular graph was correctly done, right? So that is also an interesting problem to look at. Apart from that, there are also different other settings that you could look at. Like for example, the client server setting according to me is not very well explored. There are of course ORAM based work, TE based work, but they are again very specific to a specific type of algorithms as such. And
ORM-based ones are also very specific.
like you need to like for example, the same algorithm or the same approach cannot that is used for say breadth first search cannot be used for say shortest path or something, because those works rely on maintaining certain data structures which would be different for different algorithms. Like for BFS you would need like an oblivious stack or something, whereas for say shortest path you need like an oblivious heap. Sorry, yeah, heap or yeah, priority queue or whatever. So
implementing those, I think then the key question over there is implementing those data structures.
I think there are works that have implemented those data structures, but there are very few works that have actually used that data structures for graph computations.
Okay.
Yeah, that's one thing I think. And
But do you think it's like every graph algorithm is not going to require it's, I mean, different altogether? It's,
yeah, it would be different. Like for example, like PageRank type computation, for them maybe the ORAM based approach is not very efficient, uh, right? But let's say you want to find like single source shortest path or something like that. In that case, it is like that could be more efficient. Because communication mainly, because in graffiti or graphs you'll be touching on this entire graph even though you're operating on one node, right? And also another model is like this particular model where you have a single client with some query and there is a server which knows the graph and it holds the graph, right? And the client wants to query this graph. The client shouldn't learn any information about the graph except for the query result, and the server shouldn't learn about the query. Right? A simple example could be like, you have this Google Maps, right? There is some data stored by the map data that is stored as a network by Google in its server, and you want to search for a shortest distance between or a shortest route between a point, point A to point B. You don't want Google to learn your location and what travel that you're making. At the same time, maybe the data that Google has, that it has generated, right, that is like a proprietary information for Google, it wouldn't want to share with others.
This is a very nice one. Do you have something in your
I mean, I think there are some works, I think the way to go would be like functional encryption or something that is less explored. But yeah, something like functional encryption should be useful there.
functional encryption? Would it be possible?
It is costly, but it's assumed to be more efficient than homomorphic encryption. And also recently, homomorphic encryption has also become very practical. Works and a lot of groups working on hardware acceleration for homomorphic encryption, which has made homomorphic encryption also very real time. Like there's also talk on RWC about that.
They're claiming it's practical.
Yeah. It was by
Okay.
this K in CKKS. I forgot his name, but sorry.
Chion was there.
Oh yeah, I think it was C in CKKS.
So
Yeah.
I knew that Sai Halevi and full people were working.
Sorry.
Sai Halevi and their group, his group was working on that.
Oh, okay. I'm not sure.
So this is a different.
This is a different, I think. I'm not sure. Are they from like
Are
South
they
Korea?
claiming like the generic one or for certain functions? Or, I mean, I know.
So
that
they were showing some benchmarks for PPML, like they're doing object detection on video, and they were showing that they were able to do it in real time.
Yeah.
Yeah, and they have a GPU based framework. It's called Heian GPU or something like that.
You have to rely on some strong hardware.
Right. Yeah, obviously. But that is also becoming more and more
Yeah.
practical. So for graph algorithms, I think HE based solution or FHE based solution is very less explored, or even functional encryption. So that's an interesting direction. And finally, yeah, there are also other types of algorithm which, although you can represent it as message passing algorithms, they are not very efficient. Mainly because even in clear text, these are very hard problems. Like for example, cycle detection or subgraph pattern matching, right? And also you have these incremental graph computation, which are designed for dynamic graphs, right? Wherein, like whenever graph updates, you don't have to recompute everything from scratch. You go to some intermediate state and you do some incremental computation. So it's also interesting how you can adopt something like that for MPC, right? Because it's not very straightforward to do that. Yeah. So yeah, these are some open problems, and thank you. I'm open for questions.
Yeah, yeah.
Okay, hello everyone. Welcome to the post-lunch session. This will be on the topic of private set intersection, which is a really fascinating topic. And the topic will be kick-started by Satrajit. Satrajit is a faculty member at Department of Computer Science, IIT Kharagpur. He did his PhD from Aarhus Crypto Group, which is one of the best-known crypto groups in the area of MPC. And he also did his postdoctoral research from the same group. So without wasting time, over to Satyajit.
Thank you, Ashishda, for the introduction. So I'm going to talk about sublinear PSI. And yeah, it was a surprise what is PSI, but for the audience, I think it is not. So it is private set intersection. So how many of you think that it is possible? Sublinear private set intersection. Even if you don't know the topic, just raise your hand if you think possible, 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 possible.
Sublinear.
Sublinear.
Sublinear in the
Set size. Okay, there are some possible, others maybe I have no votes for not possible. So
You are talking about it, so it's possible.
that's a good point. Okay. Okay, so then let's see. So this is like what is PSI? It's a special case of secure multi-party computation, and as we all know, what is secure multi-party computation? So where there two or multiple parties have their private input, they want to compute on that and to get some result, say A of ABC, and the goal is with privacy, that at the end no one will not know what is A, B or C, like that remains private. And also like throughout this talk, I will assume that secure channel exists, every parties are semi-honest, they are following the protocol, and whenever I talk about some communication complexity, assume that I am hiding some polylog factors. Okay. Why is this special case? Because MPC gives us generic protocol for any functionality. Given any function, you want to compute it privately, and that there comes the MPC. And in case of PSI, we only consider this set intersection functionality. And why that is different? Of course, with MPC we can do that, but if we consider that specific functionality, often we can apply certain optimizations. So that's why there are a lot of protocols for this PSI you see in the literature. So more formally, this is the functionality what we want to achieve. So two-party PSI, where both the parties will give their set SA and SB as input, and they will get back this SA intersection SB. So essentially, like after the protocol, both the party will learn this 3 and 4 on these green structures, and Bob will not learn anything about this 1 and 2 and Alice will not learn anything about this 5 and 6. Okay, good, very simple functionality. Of course, you can extend it to for multiple party cases, and there are also other variants possible. Now, how we define security? As usual, simulation paradigm, where what we show is a ideal functionality. That means if there exists a trusted party to whom you can give these sets, and it will output the intersection to one of the party. So, and there is an interactive protocol. Then what we want is that this interaction should not be able to give any extra information. Okay, that means the leakage in this ideal functionality, which is just the output of the protocol, that should be the same here in the real world. Okay, very much informally I am talking about this paradigm. So, very simple functionality, simple security definition. Yes?
Do we need to ensure that both parties get the output, or are we fine with just?
No, like it depends on the functionality. For example, here it is one-sided two-party PSI we are defining. So here one party will get the output. So essentially, depending on what functionality you are trying to implement, you will get your security, and accordingly the input-output changes. Okay. So then let's consider a very simple protocol for this. What is the protocol? Alice have this set. So it sends this H1, H2, H3, H4 to Bob, and Bob computes H3, H4, H5, H6. Compare this. Yeah.
What is H, sir?
Okay, yeah. H is some function which does not leak anything about X. Okay, let's consider it's a hash function. Okay. But how you model it, I'm not going into the technicality or anything like that. Say there is a function which gives you the guarantee that it will not leak any information about this input X. Okay, and then Alice is computing that because it will not leak any information about X. So it is like sending it, thinking that its set will remain private. And then Bob will, H is a public function. So Bob can also compute it. Bob will compute it. It will compare it and will get the intersection.
So H has to be a deterministic.
H has to be a deterministic function. Yes. Good. Now question, is this protocol secure? Who thinks secure? Hmm?
It's not.
It's not. Why?
So because that other person can also compute the H of his own elements and then.
Yeah, that's what it's doing. H3, H4, H5, H6. And then it is comparing to see this H3 and H4 is in the intersection. Right?
Yeah.
So that is the goal. That's not an attack, that's a feature.
It can also compute H1 and H2.
Exactly. So here the problem is that Bob can also check that H1 and H2 is in the list, because this thing gives a oracle access to Bob. Once Bob get this, Bob can in the offline phase it can sample all the elements from the set and then compute it and check whether that is in the intersection or not. Or in fact not necessarily intersection, it will just learn all the elements of Alice's set. Okay. So yes.
Sir, but that's very difficult now, sir. We can assume the universal set is very large, and what is the probability that one is actually there in the.
So if we are working with something where the elements are distributed uniformly at random over a large space, then maybe we can guarantee something. But still, like it can keep on computing. It doesn't have to, like later at some point, 10 years, 15 years back, it will find one element was in Alice's set. So that's a breach. That's a breach with respect to what? Think about the ideal world functionality. Okay, in ideal world, is this possible? Even if it can try to find something, sample something, and check whether that is in Alice's set, is it possible in the ideal world?
Yes, sir. In ideal world, if the Bob has unbounded computational power, then it may be.
No. How? It is not possible, because it is like it is accessing the functionality one time. Whatever it gives to the functionality, it will get the output based on that. Okay. But here, this thing gives some oracle access to Bob. Bob can later compute and get some extra output from this thing. Okay. So it's not possible. So they are not equivalent. So this protocol is not secure. Okay. So simple idea. Yes.
So is the size of SA and SB they are private information? You don't like.
Yeah. For now, consider they are not private. Know it.
Okay.
Okay. So this is not secure, but then it's not trivial. So that's why you see a lot of papers. This kind of trivial idea, like it's been implemented and it's been attacked. And whenever you try to build PSI protocol, sometimes this happens. Like you will see something will give some sort of oracle access to the other party, and that leaks some useful information from the other party. So we have to be very careful while designing this kind of functionalities. Anyways, it's just to warm up and give you some idea that this problem, though it looks very simple, it is not that simple. But it has a lot of applications. So that's why people keep on working on these PSI protocols. The first one, measuring at conversion rate. What is that? So when you go to Google or somewhere you write something, you see a lot of search results. And along with that, you will also see there are some advertisement that comes there. You click on those ads, you see what is there, and maybe you get influenced. Maybe you buy those products for some company. So now try to frame it as a PSI problem. So Google has this list of users who click on those ad of a company, and this company has the list of customers who bought that product. So now because this person looked into this thing and buy those products, the company should give some commission to Google. Essentially, it should give commission with respect to the size of the intersection. And that's how internet works. It's a billion-dollar industry. And then there comes this measuring at conversion rate as an application of this private set intersection. But this is just one application. There are many applications. You can search for it and look into that. There is this private contact discovery, contact tracing, privacy preserving analytics, botnet detection, and many more. So that's why you will see a lot of papers, like every year you will see the two-party PSI, multi-party PSI, variants of PSI, lot of papers in the literature. Every year it's coming up. So then one natural question to ask is that all these things, of course the communication depends on the size of the set, right? And sometimes set sizes are huge. So whether it is possible to reduce the communication complexity with respect to set size. And the question is, it is possible to achieve sublinear PSI? And unfortunately, no, we cannot achieve that. Because there is a lower bound result which says that you have to communicate with respect to set sizes. So that's the sad story, the end of this talk. So, but maybe I will stretch it a little bit. I will try to find some special cases of PSI where maybe it's possible to bypass this lower bound result. Okay. Specifically consider these few applications. One, there is this biometric search, privacy preserving biometric search. You give your fingerprint to some reader, there is a database of templates, and then if there is a large match with your fingerprint template and something in the database, then maybe you will get access to something. Okay. Maybe you want to date someone. So when number of preferences, like whatever preferences you give, matches with that person, and then and only then you will go for a date. Or maybe consider a ride sharing application where two parties want to go from some A to B, so they will share a ride if and only if the most of the route matches. Okay. For all these applications, one thing is very much natural, right? That is, the size of the intersection is very large. So in this application, we care about the size of the intersection, and sometimes we also don't care about the exact intersection, but to the fact that the size of the intersection is large or not. And sometimes we also want to learn the intersection if and only if the size of the intersection is large. So then we ask the question, we modify the question that what communication complexity do you need if we care about some large intersection? Yes?
How do we define large here? Is it
Yeah, good question. We'll come to that. Okay. We'll see that in a moment. But think about it, like when I say something is large, That means I already have a priori knowledge about what is large. So whenever I learn some intersection, that information is being leaked, that I learned the intersection because the size of the intersection is large. So one bit of information is already leaked if we consider this kind of functionality. And this is related to a special functionality which is called threshold private set intersection. Okay, which is again similar to private set intersection, but both the parties will learn the intersection if and only if the size of the intersection is greater than some threshold. So by large, I mean that. Okay. N minus t. What is n? What is t? I will come to that in the next slide. But the point is that this bit of information is already leaked when we run this functionality. Okay. So there are a couple of protocol like FNP04, HOS 17, Gen 17. All of them implemented this threshold PSI protocols, but the communication complexity of those protocols are linear or at least linear. In fact, there are some protocols, I think HOS has quadratic complexity in the set size. So consider size of the set is some n. Okay. But what we observe in GS19 that that should not be the case. First of all, we observe that feasibility of this threshold PSI functionality in with sublinear communication. That means feasibility of sublinear threshold PSI. So what we essentially find is the following. So consider like this is the setup, this is the set size is n, and t is the size of the set difference. So what we show that first of all we know already for two-party PSI protocol the lower bound is omega of n. For within matching up, there are a lot of protocols with matching upper bound which is order of n. For threshold PSI, surprisingly the lower bound is omega of t. Actually not that surprisingly once you look into that. And then we give couple of protocols with matching upper bound, order of t or optimal protocol using fully homomorphic encryption, order of t squared protocol using additively homomorphic encryption and something called oblivious linear function evaluation, and then using generic 2PC we also have an order of t cube protocol. Now in the rest of the talk, so I will talk about these three things, and feel free to ask questions because I am not planning to finish everything. I will just start talking and hope you will interact well so that I cannot finish it. Okay. And first I will talk about the lower bound. This is a very simple result. Then the FHE based protocol, and then the sublinear TPSI without FHE, because FHE has like lot of computational overhead. Okay. Let's see the lower bound result. Say Alice and Bob want to compute the intersection, and they have two sets of size t. The question is whether they can do it with less than t number of elements. Is it possible? So we know from this FNP04 it's not possible, but we'll see that it is possible given if we have a TPSI protocol which requires less than t elements for communication. No, okay, so here, okay, this is like little bit, the notation is confusing. So here t is n, right, because this is the set size.
Only two.
Yeah, only t elements are there.
So T is the exact number of differences.
No, this is not different, this is the set size. Here, for this next two slides, t is the set size.
Yeah.
And we are trying to do PSI, not threshold PSI, with communication less than t. Okay, so we know that is not possible, but we will show if that is possible in case of threshold PSI, then we can give a protocol for a PSI protocol as well. Okay, so it's just a very simple reduction. Yeah. So given a small o of t PSI protocol, this is, by the way, this is TPSI, and we are trying to implement this PSI. Okay, we'll show that where t is the set of set difference then actually we can do this. How? It's pretty simple. Add some n minus t elements for whatever n. Same elements. Okay. You are artificially increasing the size of the set where the difference is t. Now we know like we have this small o of t protocol for threshold PSI. So we'll just run that threshold PSI protocol, and that will give a small o of t protocol for PSI. Right? So, and that is a contradiction of this PSI lower bound. Make sense? So then we have to communicate for threshold PSI, we have to communicate at least in the size of this set difference. Okay. Good. Lower bound is good, but unless there is any matching upper bound, there is no point. So let's see this matching upper bound. So it's a very simple observation. To learn the intersection, it is sufficient to learn the set difference. We all know that, right? So, but this can be used to construct a very efficient threshold PSI protocol. Just we have to encode things properly and use some structures inside that. So let's see. Similar way, Alice encodes its elements, all these elements, in a polynomial PA of x. These a1, a2 are the roots of this polynomial, and that's the elements of Alice. Yes?
I have a small question.
Yeah.
In the previous slide, group slide, one more. So over here you're actually showing that if there exists a PSI protocol, then there's a PSI protocol where you communicate less than 3 elements.
Yeah.
But over there, the PSI protocol that you're considering is a special case, right? Where you're saying both Alice and Bob have the same set size.
Yeah, of course, for that.
Yeah.
Modulo that fact, like we are considering for n elements. So the lower bound is like minimum of the set size. So the actual lower bound of what it said. Okay. So yeah.
So you're kind of considering they both them have the different distinguished.
Different distinguish.
Like two different. Okay, no, if they are same, then okay.
Yeah. Okay. So okay. So now let's start encoding. So we'll encode this Alice's element in this polynomial PA and Bob's element in this polynomial PB. So the elements in the set are root of this polynomial. Okay. So then observe that if we divide this polynomial, then the roots of this P intersection that will cancel out. These are the common roots. And then we have this something PA minus B by PB minus A, this rational function. So we start with the rational function of degree n in both in numerator and denominator, and now we have a rational function of degree t. So if the intersection size is large, then most of these roots will cancel out, and then we have a small rational polynomial, and 2t evaluation points are sufficient to determine this PA minus B or PB minus A separately by doing rational interpolation. Okay. So then suppose after rational interpolation you get this PA minus B and give it to Alice, then from this PA minus B Alice can find SA minus SB, and finally it can learn the intersection by locally computing SA minus SB. Okay.
So you are going to tell us the protocols?
Yes, more or less I will not, but I will pretend that I am telling you the protocol. So you will see.
No, so I mean each of those inputs, and then how do you find out this division PA by?
Yeah, that you have to do a little bit carefully. Okay. So in general you can think about, you can apply generic MPC to divide it, right? Like you can always do that. But then the cost is too much, then you have to reduce that cost somehow.
Right.
So yeah, tell you that I'm going to tell you the protocol without telling it. So this is that. So now the protocol is that Alice encodes its set SA into PA, give 2t evaluation points of this polynomial in a secure module, Bob encodes SV in PB, give 2T evaluation points in this secure module, and inside this secure module you will do this. Okay, why 2T? Good question. Yeah, so here the degree of the numerator and the denominator both are T.
Yes.
So they are like T coefficients we need. So then think about it as system of linear equation you are getting like from evaluation of this PA by PB. So that's a system of linear equation with 2T variables. So that you have to solve to do this rational interpolation.
You need 2T plus 1.
No, yeah, because this is monic we know.
Oh, yeah.
That's why it's 2T. Okay, and then we will do this rational interpolation inside this secure box. Okay, we are dividing, doing all this processing inside this secure module, and then we'll check some consistency. Consistency because we don't know whether the size is actually large or small. With the consistency check, we can say with high probability, okay, they are the same. And if that passes, then the secure module will output PV minus A to Bob and PA minus B to Alice. Okay. This is the protocol. Any question?
Which one? Module.
Basically,
Everything, right?
Yeah, green box.
Sure. Like the green box. Read the paper, but that we also didn't write it there. But no, like this is simple. Like this is a secure module.
Yeah.
You are doing rational interpolation inside MPC.
Yes.
There's like nothing to write about. But anyway, so the point is that you have this 2T evaluation points. So you have to do all these divisions to get this equation, and then you have to use some solver to solve this. You can use MPC, but say generic 2PC, but the communication complexity will be order of T cube. Why? Why T cube?
Matrix multiplication.
Yeah, more or less, but you have to solve this, do say Gaussian elimination. So T cube multiplications you need. So there will be, this complexity will be proportional to T cube. With FHE order of T, of course, you are not doing it now by interaction. What you are doing, maybe Alice can send the encrypted evaluation points to Bob. Bob now locally doing the this rational interpolation. So it's computationally heavy, but communication complexity will be this order of T ciphertexts. Okay, and that gives, but that's fine. That like this FHE order of T, that's already give a matching upper bound protocol for this threshold PSI. Okay, any questions so far? No. Good. So then the question is, of course, can we do better than generic MPC? Sorry, generic 2PC in terms of communication, but without FHE. Also computationally, we don't want to do T cube multiplications. So for that, we divide this in two parts. One is a cardinality test, and then
Have another question.
Yes.
So when you say order of T,
Hmm.
you are ignoring some multiplicative. So order of T, like elements from the set.
no, order of T ciphertext you have to send.
That's
Yeah, and then there will be some expansion factor.
But your lower bound is for order of T1.
Oh, okay. The lower bound is for
Theta T, elements from the
intersection difference.
I mean,
element,
it's
yeah.
actually the elements from the set.
Yes, from the set.
Where you are picking your
Yes,
elements from.
yes, yes.
So there is a factor difference.
Yeah, there is a factor difference, and that's why order is like us to save us. Okay. Yeah. Okay. So now we considered in two phases this threshold PSI. One is cardinality test, where we check whether the intersection size is large enough. If it is large, then we have given a protocol which is very efficient to find the actual intersection. Okay. And in GS19 there is this T-square communication complexity protocol based on additively homomorphic encryption for this cardinality test part, and that's why the protocol we get is order of T-square. But given this, we have a very efficient protocol with order of T communication complexity. But this is the problem, right? So let's focus on this. Any question before we jump into the next part? Okay, yes, no. So like what is the current status? Like there are like lot of protocol, essentially 4 protocols which consider this sublinear threshold PSI problem, and all these protocols give some cardinality test with order of t square communication complexity. This BMRR21 has one protocol with order of t communication, but that is a very different functionality. That's not exactly the threshold PSI functionality we are considering. Okay, or which is more natural. They are not considering that. But the good news is that given any of this protocol, we can compile it to a protocol with order of t communication. Okay. Essentially, given any protocol with poly t communication complexity, we give this in GS23. We give a compiler which will give a protocol with order of t multiplied with some delta or some constant delta communication complexity. Okay, let's see how it works. So again, so we take any cardinality testing with poly t communication. There are, I think, or not any cardinality testing, any sublinear cardinality testing with poly of t communication, where t is the size of the set difference, and which gives secret shared output. So all the protocol in the literature, they don't give secret shared output, but it's easy to convert it which gives a secret shared output. So once we have that, and which has
Shared, you mean the bit of the cardinality basically.
yeah. Cardinality is a bit, just that bit should be secret shared. Okay. So then can apply this compiler, which fails with some probability 2 to the power minus delta. Then you can have this delta some 40 or something like that. Then we have a small constant for t, and then that will have order of t communication. Okay, I could have hide delta. Come on, like I write it for the sake of it. It's order.
But it depends on your probability. So
Yeah, I say okay, the probability is small, and sure. Okay. So what we do in this protocol? So it is essentially we are using a divide and conquer approach. So consider these are the set elements, and these green balls represent the elements which are in the intersection, and the red ball represent the elements which are in the set difference. So they are not the same. So Alice and Bob throw this in T buckets randomly. Then in expectation, like each of this bucket, the size of the intersection will be large, if the intersection size is large to start with. Okay, so if there are P elements in the difference, and if we throw randomly, then in expectation, each bucket should have one element which is in the difference. Okay, that means the other elements are in the intersection. So we are just doing that, throwing elements, and the distribution will follow. Okay, but in expectation, that is important. Okay? So then the protocol is simple. Like now we have small instances of the same problem. We apply this protocol for cardinality testing for each bucket. Okay. But that will not give us anything, because that essentially gives us a secret sharing of 1 or 0 for each bucket. What we want is to compute for cardinality in each of these buckets. Okay. That means we want this functionality where we give SA and SB, and it will give the secret share of the size of the intersection if the intersection is large enough. If not, it will share some default value V. Okay. But then how to do this compute cardinality module? How to build this? Any idea? Okay, maybe like it's simple, you could have think about it. But so just use cardinality testing in this way. Say we ask the cardinality testing that whether the size of the intersection is greater than or equal to n minus 1. It will say no. Okay. I'll query again whether the size of the intersection is greater than n minus 2. If it says yes, then the intersection size is n minus 2. Okay. So we just invoke this cardinality testing protocol multiple times to actually compute the cardinality in each bucket. And why this is not expensive? Because we have T invocation, T is already small. If within T it does not happen, then we don't care. Okay, because in any case we will return a default value. Okay, so this is the basic idea. So we use that, compile a protocol for this compute cardinality and deploy that for each bucket.
Wait, what is the bucket size? I thought it's
No, we have T buckets.
T buckets. Okay.
Yeah, yeah. But the communication does not depend on the size of the bucket essentially. It depends on the size of the red balls in the bucket.
Difference.
Yeah, difference. So because T is small, in expectation in each bucket that proportion of red ball is 1 or maybe close to that. So then the communication in each bucket, we want to depend it on that small threshold. Okay. Okay, good. So we will use this compute cardinality in each bucket. What is the output of compute cardinality? It is the difference. No, there is not the difference. The compute cardinality gives the size of the intersection in each bucket, or secret share of the size of the intersection. Okay. For example, here the output will be 1, 1, 2, secret share form. Okay. Once we have that, what we are going to do? Add. Simply add and run a very small module to check whether this is big enough or not. If it is big enough, we output big, otherwise we will output small. Okay, any question in this last 2-3 slides? So essentially what we are doing, we are partitioning the set into T buckets. For each bucket, we are running this compute cardinality. This compute cardinality internally using this cardinality testing protocols. And then once we have that, we have a small MPC module to sum it up, sum the size of from this each of this compute cardinality and check whether that is big enough or small. Okay?
I have a question.
Yes.
When the compute cardinality doesn't, the number of times you are invoking the cardinality testing leave information about the size of the intersection?
No, not really. Because this is parameterized.
Okay, you will run it for
T times.
Yeah.
Exactly. So it will not leak any information.
By the way, T is everybody's knowledge? Like
Yes. That's the functionality is parameterized in that threshold. Yeah. Okay. Any other questions?
That's why not
Yeah.
general.
No, not for general. Yeah, that bit of information we need. So yeah, this is the general framework which gives us the result. But note that this works if intersection size in each bucket is large enough. Okay. So in general, in each bucket we have a very small threshold, and we want the distribution to be perfect once we throw it. And if that is the case, then this protocol will succeed. But it might be the case that in one bucket, this is not the case. The intersection size becomes small, and then it will output garbage. Right? And then even if the size of the intersection is large enough, this cardinality testing will output that it is not large enough, it is small. Okay? How to resolve that? repeat, that's the delta which I wanted to hide. So then to amplify this, like we'll repeat this protocol. So say in the first invocation it says it is small, it's not big enough, it's small. But if it says big, that means it's big, like it hits that distribution. So and the size of the intersection is indeed large. And then the protocol will output the size of the intersection is large. Okay? So that is the overall idea of this two-party threshold cardinality testing protocol. We also extended this, okay, yeah. So when we instantiate with GS19, there is the order of t square protocol. With a threshold of order of log t, we get this order of t, like polylog, sorry I forget to remove this. So yeah, so from order of t square, we'll get a protocol with order of t communication complexity.
What is the first one?
This one, this lambda, this is security parameter. Lambda square is also small. It's super practical, believe me.
If lambda is small, then lambda square must be small.
No, that was delta. You are confused. So okay, so this is the two-party protocol. Ignore those lambda square deltas. It's nice from t square to t. Think about that. And then for the two-party, it was little bit easier to deal with because large intersection means small symmetric set difference. But for multi-party case, that is not the case. We have to talk about this intersection size directly. So for that, like look into the paper, like how we deal with that. You have to do some padding carefully and have to see that whether leaks any information or not. But that is all there, that's been done, and we for the multi-party case also, we'll get a protocol with order of t ignoring lot of things protocol. So good. So we have the first part done, and once we have the first part, we jump to the next part. That means we want to compute the PSI given the intersection size is large. Okay, let's see the protocol again. So what was our idea, that we divided PA by PB, that will give PA minus B and PB minus A. And if we want to give it to Bob, or maybe we want to reveal this part to Bob and not this part we want to give to Alice. Like that was the thing, because and that's how the protocol also worked for this using FHE, 2PC and everything. But then what if we somehow randomize the numerator and then give the whole rational function in plane to Bob? Okay. The main reason of like we get bad complexity, because we have to do either something inside FHE ciphertext, this rational interpolation, or 2PC. Okay, that is also again depends on the circuit depth of that specific rational interpolation circuit. So then if we can do that, then that will be awesome. Let's see how to randomize it. So we just multiply this PA and PB with R and S, which is a random polynomial. Again, this P intersection, these factors will cancel out, and we will get something like this. So from this, we'll get this. Here, important thing is that this degree of PA minus B and PB minus A is at most T. Why? Why this is at most T?
That's the difference.
Yeah, that's the difference, but we also run this previous part, so that guarantees that this has degree at most T. So this is important. Okay. And then if we choose this R and S to be a degree T polynomial, then this numerator is distributed uniformly at random in the space of for 2T degree polynomial. Okay. So if we can do this thing somehow and give it in plane to Bob, then it will not leak any information.
We are giving the whole thing.
The whole rational function. So now instead of doing the rational interpolation inside a secure module, we want to compute just the rational function. Okay.
The numerator is
sum of two reducible polynomials.
This sum of two reducible polynomial.
Because Rx and that is they constitute the factors of
Rx and Sx are random polynomial we are
So
sampling.
if you take the first term, P of A minus Px into R of x, they constitute the factors of a 2t degree polynomial.
Yes.
So how can you say numerator is a completely random 2t?
Yeah, so there is a proof for that. In fact, there are two proofs for that. One was in case 05, like this one, and like we have also separate proof for that. So we can probably say that, okay, if we use this t degree random polynomial and mix it in this way, so that will indeed give a 2t degree random polynomial.
You are saying it is always going to be a
Sum
reducible.
Sum of two reducible polynomials.
And also like GCD, okay, another thing is GCD of this and this is 1. Okay. So GCD of this PA minus B and PB minus A is 1. So there is no common factor here. That is also important in that proof, like when you prove that this is indeed a uniform random 2t degree polynomial. Okay?
So it is like totally random.
Yes, it is totally random. So then again, protocol blueprint. So, but now we need a little bit more points. So essentially 3t points to do the rational interpolation, but that's fine. So now again, SA encode its polynomial PA, give order of t evaluation points to the secure module. Bob encode PB or encode SB in PB and give this order of t points, and then we'll evaluate all these points of this rational function essentially. So we'll not do the rational interpolations. That is the important part. That means some constant number of multiplications, like 1 inverse. Also inverse is not required. Like I think 3 multiplication. 3 multiplication you have to do inside the secure module for order of t points. So you use your favorite MPC multiplication protocol with constant overhead. We use OLE for that purpose, and that will give this evaluation of this Zx or Z of alpha I to Bob. So once that is given, Bob will now do this interpolation in plane and extract the B minus
So
A.
there is no error in correcting.
Hmm?
There is no error in correcting.
There might be some negligible error, like when it, like in general, no, like why?
No, because of multiplying by two random things.
Mm-hmm. So we don't care about this thing, right? So just going back.
Don't care about the.
So we are doing this in the protocol.
Yeah,
So that results something like this internally.
yeah.
Okay, and we want this.
How are you extracting this one?
We are doing rational interpolation again. We have evaluation point of this rational function over sufficiently many points. We are solving system of linear equation.
3T?
Hmm?
3T.
3t, yeah, 3t.
And then you are solving it.
Solving it for like 3t points means like here the degree is 2t variables, and for this t variables we are solving
So
this.
Bob is getting entire Z polynomial? Z.
Yes, yes.
And from there, how?
There, from there it will extract both the numerator and the denominator.
It's like the same thing, error correction codes, whatever you do for
Right.
recovering back the polynomial.
Right. And from there it is?
From there, this is not useful. Okay, it will also find this, but because this guarantee is there that this is uniformly at random, it will use this PB minus C those variables from that, and that will give the intersection to Bob.
So are you telling that RNS don't have a common root?
Yeah, that's when.
No, yeah, like you cannot say something like that. You are sampling randomly. It cannot.
Okay, but then if they have a common root which is also there in PV, then it can potentially.
Yes, so that's why like there might be some problem.
This is why I was.
Yeah, exactly. That's why I said that there's some negligible chance is there that there will be some problem with the correctness. But then you have to sample randomly, otherwise you cannot guarantee, right?
Yeah.
Yeah.
But that automatically introduces
Yes,
some
yes,
error.
yeah. Okay. So that's the protocol, and then yeah, you use any MPC module for this constant number of multiplications, and that will give a very efficient order of T protocol for this threshold private set intersection. And so yeah, this is again overall, like for the cardinality test, use any order of T cardinality test protocol, use this GS23 compiler, and then once you are done with the cardinality, if it is yes, if it is no, you will abort. If it is yes, you go to the next stage, use this protocol to get this order of T communication complexity protocol. So and that essentially gives this sublinear threshold PSI. And yeah, and these are the 4 papers related to these topics. Feel free to read this. Okay. Thank you.
Unfortunately, you finished the talk.
Yeah, I see. Like I was a little bit fast. Should I explain something again? Yeah, any question?
You want to extend it to beyond two parties?
No, okay, like this. So these things have multi-party variants. So for
But then how do you encode polynomial and then do the division?
so like what we do is a star topology, and then one party will divide. Okay, so you combine all the polynomials in the numerator, and then with one factor you divide, and then that party will get the intersection. Okay.
You can achieve the same communication process for the multiple.
Yes, so there will be a factor of number of parties, but yeah, per party you'll get the same thing.
What are the challenges for malicious security?
Many challenges, I would say, because we are doing lot of things which we have to ensure, and
The encoding of the polynomial.
one thing, first the encoding of the polynomial, maybe we can put also some zero knowledge on top of it, like that's a very inefficient way to do
Just
that.
ensure that the top most coefficient is 1.
Mhm.
Does it already imply encoding of a valid set?
Oh, what do you mean?
No, so this polynomial PAX,
Mm-hmm.
it will have 1 in the highest order.
Yes.
I guess.
Oh, okay. Like that. If we do this thing, then that will remain, I think, because it depends on how you are sampling R and S. So it does not depend on the sampling of PA and PB. So if you ensure that R and S is random, so at least that part can be ensured. But I think the problem will come if we trying to prove this in UC framework, because like we are communicating much less compared to the set size, then extraction might be a problem.
Extracting the elements.
Yeah, maybe some different other definitions of weaker definitions of malicious security is possible to achieve, but I'm not entirely sure. Then maybe we can you can give a functionality in that sense that the specific functionality can be achieved. But for just for PSI functionality, it might be.
People have not done malicious security.
No.
Huh?
No.
This why people have not looked at malicious security.
No.
Seriously.
At least I don't know. Okay, so then I have to see. Now you are telling seriously.
So one of the applications was like the ad conversion thing, right?
Yeah.
Where the parties have incentive to cheat.
Mm-hmm.
Google doesn't want to give vulnerability, right?
Mm-hmm. Oh no, malicious security for PSI is there. So I'm talking about this sublinear threshold PSI malicious security. That of course, like PSI malicious security, like there are a lot of ones. Yeah, and it is not like also the difficulty I was talking about, like about this specific functionality. Yeah.
You are right. I mean, we are committing a lot less, so there is a lot of freedom left.
Yes, exactly.
Maybe this is something inherent that you cannot achieve.
Maybe, yeah. Or maybe some you have to change some definition and then achieve something. Okay, any other questions? Yes.
Are there any works? All of these works, I think, are achieving like constant rounds. You can realize them in
Yeah, yeah.
But are there any works which say takes rounds which are like maybe logarithmic in the set size or something, but better communication, something like that, either with threshold PSI or PSI?
Can you go beyond sublinear first of all, and then at the expense of more round
I
numbers?
don't think you can go beyond sublinear, but maybe at least you can reduce the constant overhead.
Round complexity you can reduce it,
No, increase the
or increase the round and then further reduce.
concrete communication.
Okay. Yeah, I don't know of anything like
You all
that.
your delta
Yeah, yeah. Yeah, like for PSI there are many protocols with like multiple rounds, but then people try to reduce number of rounds usually. And in PSI now the protocols are pretty efficient, like in fact concretely efficient. You can implement in few seconds for 10 to the power 20 elements you can do. So those things are there. But for different functionalities, maybe there is something scope of work. Okay.
So both for PSI as well as threshold PSI,
Mhm.
if we forget about sublinearity, and let's say we want malicious security, then what is the best known
Best known. Okay.
in terms of communication?
For threshold PSI, I think this is the set. There's at least for sub. Oh, you forget about sublinear. Even if you forget about sublinear, you can actually compile any efficient PSI protocol to threshold PSI in certain way. Okay, you just have to have a one module, one gadget which will check whether the size of the intersection is large enough or not. You say consider your favorite circuit PSI which gives the secret share, and then you have a module to check whether the size of the intersection is large or not, and then accordingly you output the shares. So that will give a threshold PSI protocol. So if your circuit PSI is very efficient, then that will transfer. Very efficient concretely, I means like whatever people.
Linear or what is it?
Yeah, they're linear, of course. Yeah. So if you forget about sublinearity, yeah, there's only like linear protocols, and some protocols are in fact quadratic.
Maliciously secure as well.
Yes, there are maliciously secure linear complexity protocols for PSI. Yeah. Okay. I guess no other questions.
So we can take the questions offline and then let's thank the speaker. Just 2 minutes and then we will start.
Sure.
Oh, there is one more. So for this talk, since it's online, your questions may not be audible. So wait for the microphone.
Okay, so hello everyone, welcome back after the break for the second talk on private set intersection. So our next speaker is Dr. Vutichai. He's going to join us online. The title of his presentation is Private Set Intersection, PSI Payload and Fuzzy PSI. So Assistant Professor Vutichai is a faculty member at the Department of Mathematics and Computer Science, Faculty of Science, Chulalongkorn University in Bangkok, Thailand. His research is in cryptography with a particular focus on secure multi-party computation. His recent work emphasizes PSI and its variants. He is also interested in other areas of cryptography, including homomorphic encryption, zero knowledge protocols, and consensus protocols. Before joining Chulalongkorn University, he served as a postdoctoral researcher at the University of California, Los Angeles, UCLA. He earned his PhD in mathematics from UCLA and holds a BS in mathematics and a BA in computer science from Duke University, both in the United States. So without wasting much time, over to you. You can start now.
Thank you for introduction. I assume that you already attend the previous session that we talk about the PSI already. So I will kind of skip the definition of PSI and just go straight to the more specific construction that involve that allow the payload to be transmit. And in the second half, I will talk about the fuzzy PSI, which is somewhat new variant that is gaining popularity these days. So the last few like conference, top tier conference actually have a few papers in fuzzy PSI. So yeah, so I will briefly like kind of review the basic concept of PSI and a few variants, and then I will focus on like basically two techniques that involve that allow the payload to be transmit along with the result. And then in the second half, I will switch focus on switch the focus to the fuzzy variant of PSI. If you have any question, feel free to ask or like interrupt. So the basic setting of PSI is basically we have two parties. I mean, there are also like multi-party version of PSI, but in this talk, I will mainly talk about the two party variant. So say Alice and Bob, both of them has some set of elements, and they want to find the intersection between their sets, right? This is the standard setting of PSI, and the security requirement is that they will only learn the intersection, but not the other elements of other parties. Say, for example, Alice if Bob is the receiver, he will only learn the intersection between his alignment and Alice, but Alice will learn nothing. So we also focus on the case when only one party that learn the result, another party will learn nothing. There are also other variants as well that both parties can learn the result, and so on and so forth. Yeah, so this is the basic variation of PSI that that we want to construct. Of course, PSI is a special case of like two-party computation. So we use the definition of like the standard definition of two-party computation to define the security of PSI, like the real world, ideal world paradigm and such. But I assume that you probably have heard from the previous session already, so I will not go into the details. That means when we want to talk about the security of or the definition of what each variant of PSI, we want to use the functionality definition. For the standard PSI functionality, we can just say that the sender may send say Alice send her set and Bob send his set, and then the functionality compute the intersection and then send it back to Bob, who is the receiver. In this case, of course, Alice will learn nothing and Bob will learn nothing other than the intersection, right? In most of the construction for the PSI, actually, I haven't very follow the newer and newer like progress on the standard PSI. So, but I think most of the construction have some upper bound on the set size, like as a part of the functionality. So basically, the actual functionality may look like there is an upper bound on the set size of both parties, and this can only submit a set of a certain size. Bob can only submit a set of certain size, and then the functionality only allow to compute the intersection when this set size are satisfied. There are a lot of application of standard PSI, as you probably have learned from previous talk. For example, we can use the PSI to analyze data in, like, say, online advertising. Alice may own a store and Bob may own online retail. So they may want to find the common customer that went to the store for Alice and visit the online website. In this case, they want to know the intersection between the set of their customers, right? And in this case, in the real world application, both parties does not want to reveal the entire list of their customers. So the way that we can find the common customers without review the whole set is basically use the PSI, right? So PSI allow Alice and Bob to compute this intersection without reviewing the entire list of their customers. In some case, they may want to hide the identity of this intersection as well, but only want to learn about the size of the intersection, right? So in this case, we will have another variant of PSI that specifically compute only the size, but not the identity of the customer. Sometimes one parties may also have associate information. For example, how much each customer like in the store, right? For example, Bob may have may have the information about the number of like the amount of money that each of his customer store, and Alice may want to learn the these numbers for each customer that they share, right? In this case, we will define this associate information as payload. In some case, Alice may yes. Yes, there is also, yes, there is the one where only size of the intersection is reviewed. Yes. Uh-huh. In terms of like asymptotic efficiency, I would say it should be the same because I mean there are solutions that solve PSI in basically linear efficiency. If you want to learn about the size of the intersection, you basically need to look through all, the whole list anyway, right? So in the symmetric case where both parties have about the same size, in this case, you cannot avoid the linear complexity. But in terms of the practical efficiency, I would say yes. So because you don't need to actually the difference should not be that much because yeah, you only need to learn about the size, so you don't need to basically but you can also think of that as you want to hide the identity as well, right? So hiding the identity actually can be thought of as like more secrecy. In this case, yeah, I would say the trade-off should not be that much. But I haven't actually studied the we call this version the PSI cardinality or PSI CA. I haven't studied this variation in detail, so I'm not sure if there is a significant improvement. But the last time I read the paper on these topics, the difference is just more of a practical part, but not the asymptotic part. Yeah, another variant is when you have extra payload, right? Which are the extra information that only one party has, and you want to another party want to learn this information. So this is actually extra work that they actually need to compute. So you can either send this information. I mean, you can obtain this information for every single elements in the set, or you can actually do some further computation on this. For example, you can add them up and only learn the sum. We also have this variant of PSI sum that only learn the sum of the payload. So yeah, here is the more precise functionality that I mentioned earlier. For the PSI payload functionality, we have one party with not just a set. So a list has set A as before, but a list also has the payload associated with each alignment in A, right? And Bob only has set B. So payload is in only one party, basically the sender. And in this case, Bob wants to learn the alignment in the intersection and also the payload that associate with that alignment, but not other payload. basically the payload associated with alignments not in the intersection, Bob should not learn about it, right? So this is basically the variant that that is very interesting because you can actually use this to use this functionality as a sub protocol more ways than the standard PSI. This payload can be extra information that you may need to do other computation, and after Bob receive the payload, he can actually further compute on this payload to get like other thing that you want from the sub protocol. We will talk about this later in the fuzzy PSI because I actually have a protocol that rely on this payload to further do the fuzzy PSI. Yeah, and in some case you may want to learn not the payload but the sum of the payload without reviewing individual payload. In this case, the PSI sum is also one of the common functionality or common variant of PSI that people study. Most of the case though, this PSI sum actually leaks extra information, which is the size of the intersection. Note that you can see from here that PSI sum does not reveal the intersection at all, right? So Bob will not learn alignments in the intersection, but only learn the payload. But in most cases, most of the construction of PSI sum that I know also reveal the size of the intersection in addition to the sum of the payload. So this is actually the leakage. Exactly. So if all T are all of the payload are 1, right, then you basically get the cardinality. But of course, using the PSI payload to do or PSI sum to do the cardinality is kind of wasteful because yeah, this is certainly worse than the standard PSI. Yeah, so the variant that we talked about earlier is the PSI cardinality. Actually, sometimes it's abbreviated as PSI-C, but usually it's CA. So yeah, this is probably not as common. Yeah, you can define the PSI cardinality where the receiver only learn the size of the intersection, but not the intersection itself. And yeah, each of the variation actually have several techniques that better or worse for them, including the variant that we probably discussed earlier in the previous section, which is the unbalanced, right? So the technique that usually used in unbalanced actually are different from the balanced case. I will talk about a few techniques or a few approach that that people usually use to construct the PSI that also allow the payload to be passed along. The first approach is using the oblivious PRF. So oblivious PRF is basically a PRF which basically give you a random numbers when you plug in some input, right? So I use these Greek letters as random numbers. Basically, a list can compute the output of the OPRF for her set, but the OPRF has the one party can actually construct the OPRF basically in the most of the standard construction. A list will actually evaluate OPRF on any alignments that she wants. But on the other hand, the receiver or Bob only allowed to evaluate the OPRF on a certain alignments that is fixed in advance. So basically, Bob can only learn the output of OPRF on his input sets, right? So once the OPIF is constructed, Bob can no longer compute the output of OPIF on something that is not in his set. For example, if 97 is not in Bob's sets, then he cannot compute the OPIF of 97. Basically, lock Bob to only learn about the output of the OPIF on his sets. In this case, Alice can just send the output of her, and Bob can just select which one match with his own, right? In this case, Bob can actually find the intersection. Once Bob learned all these random numbers, Bob can see that numbers that match between his sets and Alice's sets, right? So he learned that the numbers that map to these 4 random numbers basically are in the intersection. So this is a way that you can construct PSI from oblivious PIF. And there are several ways to construct, yes. Yes, it's a key function. So you can think of Alice obtain the key, while Bob only obtain the result on his set, and does not learn the key. That's how Alice can use the key to compute the output on any of her alignments, but Bob cannot. Alice hold the key. Yes, and Alice hold the key, and Bob only learn the result on his input sets. Basically, OPIF is an interactive protocol. So most of the construction is interactive protocol between Alice and Bob. At the end, Bob will learn the result of his choice, and Alice learn the key. And once the protocol ends, Bob can no longer obtain more results. That's why he cannot test for Alice alignments once Alice send her alignments over. Right. If depends on construction. I think most of the construction, there are symmetric key construction that come out later. I'm not sure if the one that I sent as a reference. Let's see. Where is it? Nope. Yeah, we need to check yeah, the most the more recent construction actually use some coding technique. So I'm not sure if the underlying properties. I mean, there are construction that use the oblivious. I mean the oblivious linear evaluation or OLE. Evaluate pretty efficiently. Yeah, I will check that information if that's the case. Another way that you can use this result of OPIF is to use the Gabo circuit to match them, right? This actually allow you to compute other information as well along with the matching. Basically, this will lead to another. I wouldn't call it's actually a variant of PSI, but is also the construction technique as well, which is the circuit PSI. I will talk about circuit PSI briefly in the next few slides. Here. So the idea of the circuit PSI is that Bob and Alice has has a set and some associated information. You can see that this naturally lead to the payload as well. You can have this X and Y be the payload, or you can have this X and Y be the random output of the OPIF. The idea of the circuit PSI is that you can actually use, after you compute this like X and Y, you can use the circuit PSI to basically do any further computation on this result, on this intersection of the result. Basically, you can basically construct a secret share of the result without any party learn the output of the PSI at all. For example, Alice and Bob may use the circuit PSI to output a secret share of like indicator vector, whether the ith alignment is in the and they can also compute the secret share of the concatenation of this associated information as well, which is basically you can have it as payload, right? So in this case, they can further compute on this result, and you can basically get any variation of the PSI from the circuit PSI. Okay, so circuit PSI is a very strong approach to do the PSI, but you actually need to do some additional step before you actually fit into the like the Gabo circuit. One approach that can be used together with the circuit PSI is using the oblivious key value store, or OKVS. So the idea is actually kind of related to the OPIF. For the OKVS, one party will construct the encode from the key values pair. So KIs are the keys and VIs are the values, and you can encode these key values to some structure E, and then another party can decode it in the way that if he tries to decode using KI, he will get VI. So basically, this encode store the pair with KI and VI. On the other hand, if these VIs are random numbers, then the encode of KIVI and KPalmIVI are indistinguishable. This basically imply that the E somewhat hide the information about the key if the values are uniformly random. There is also a stronger version of the value store where the output of the encode is actually indistinguishable from some random numbers of values. So basically, they encode it using a larger number of values, and it's called doubly oblivious. It turned out that you can actually construct a circuit PSI using VOLE and a more complicated version of OPIF, which is OPPIF. OPPIF is actually very similar to the OPIF, but Alice, or the one who actually get the key, can actually program some pair of input output to the OPIF, essentially similar to the OKVS. That means the OPPIF in the previous paper can actually be replaced by the OKVS in the more recent construction, and they actually improve this OKVS construction quite a lot. So I think the most recent standard PSI is actually use this technique to construct very PSI. Basically construct the efficient OKVS and then just compile it using the circuit PSI. So in this case, you can actually transfer the payload very efficiently by basically program the payload into the randomness, right? So instead of a total random number, you hide the payload inside this random number, and then Bob only learned the payload when he actually learned the mesh. Yeah, so basically, this is one approach that you can send the payload over to the other parties. Yeah, and you can use circuit PSI to compile this further to basically split the payload into secret chat and then further compute on the payload as well. The second approach is basically use algebra or polynomial. You can actually construct PSI from polynomial technique. Basically, if you assume that the alignments are in some finite field, right? Each party can actually construct a polynomial that has his alignments as roots. So basically, fx when you plug in any alignments from a list set will become 0. Similarly for Bob. The idea is that if you can construct a linear combination of these two polynomials securely, then the receiver can actually test for alignments in the intersection, because if you plug in any alignments in the intersection, both f and g will be 0, and evaluate the linear combination, in this case h, will evaluate to 0, right? And Alice can further marks her polynomial using some random polynomial r. So in this case, Bob will learn. Bob cannot compute fx because he does not know r, right? You can construct PSI. The idea is actually somewhat similar to the previous PIF in the previous technique, but in this case we have a more controlled structure, which is the polynomial, right? But how to obtain this linear combination? In the first idea that introduced this concept of polynomial-based PSI, they use FHE, which is inefficient. But basically, this get the result because you can evaluate on any alignments. If Bob plug in the numbers that is not in the intersection, he will not get 0 because it will be 0 only on G part, right? If the result is not 0. And he can easily compute the intersection by plug in all his alignments and select the one that evaluate to 0. Another more efficient way that you can compute this linear combination is by break it up into smaller parts. In particular, you can use interpolation to reconstruct the polynomial from a number of evaluation points, right? So instead of trying to find hx right away, Bob can try to compute SCI and let's say 1 plus degree of the polynomial, then Bob can use interpolation to recompute this polynomial. And you can actually compute the evaluation point using OLE. So what is OLE? OLE is basically a generalization of OT, right? So if the degree is say if the degree of f is n and the degree of g is n, right? So let's say the degree of I is also n. In this case, the degree of s will be 2n, right? So in this case, Bob will need to know 2n plus 1 evaluation points in order to interpolate the polynomial. Yeah, which this can be computed using OLE, which is basically oblivious linear evaluation, one party input A and B and one party input X, and learn AX plus B. Yeah, I think this should be 2n plus. I see. Because the degree of f is actually n minus 1, right? Yeah, there is probably plus 1 somewhere around here. Yeah. Yeah, I think this is probably at 2n plus 1. If the degree of f and the degree of g is n, you will need it's basically 1 more than the degree of h that you need. Technically, you can mark the leading coefficient. You can basically multiply the whole polynomial by a random alignment, marks the leading coefficient as well, right? Yeah, you just need to have the polynomial evaluate to 0, so the leading coefficient can be any number. Yeah, so this is one way you can obtain the PSI. You can actually improve this a little bit further by move from the polynomial over a field to a ring, right? So basically, you can actually construct a variant where both x and ab are ring alignments, and which ring that we want to use, we can use the ring of polynomial modulo some px. In this case, you will basically get something a little bit more efficient than this OLE variant. Yeah, so you can actually construct ring OLE from random OLE using basically some algebra, and you can actually set up the random OLE pretty efficiently using various techniques. These are pretty old, so yeah, basically these are from my PSI from ring OLE. So I'm pretty sure there are more recent OLE setup that you can use. Okay, so yeah, this as a result, you basically can construct this linear combination right away using fewer numbers of OLE, I think. And you can do it in the setup phase as well. You don't have to do the OLE in the online phase. Online phase, you just send a few polynomials around. So basically, this method move all the OLE to the offline phase. Yeah, and this is one way. So how does this relate to the payload? So it turned out that you can transmit the payload along with this computation. Yes. Slide this one or previous one? This one. algebra. Mhm. Yes, exactly. You can use this method for any OLE because you can think of ring standard OLE as a special case of ring OLE, right? Because a field is also a ring. Yep. Yeah, I think I need to hurry a little bit. So yeah, here is how you use the polynomial-based PSI to do the PSI payload. For Bob, he basically compute the polynomial in the same way, right? So GX has BI as roots, but for Alice, she can actually attach the payload to the polynomial. So instead of can compute fx that evaluate to the payload and concat with 0 in the front. Okay, so this 0 in the front need to be sufficiently large so that it's unlikely to occur like randomly. And if Bob has the linear combination on any alignments in the intersection, he will learn that the result actually start with a lot of zeros. So which is unlikely to occur randomly. In this case, Bob can also conclude that the number in this example, 27, is in the intersection and 5 is the associated payload, right? So this is how you can transmit the payload along with the intersection using polynomial-based PSI. Okay, so and there are also constructions that basically combine the polynomial technique and the OPIF technique, which will be somewhat more complicated. Okay, so this is the first part of my talk. Any quick question? Mm-hmm. I would say the most efficient for PSI these days are the one that based on OKVS. I think that's my most recent information. So the OKVS based PSI are the most efficient, and I'm not sure if there are more like more recent papers that basically beat this one. Yeah, I think this is probably the most efficient that as far as I know, but it's like in like 3 a new one that I am not aware of. What is the question again? Sorry. Mm-hmm. Yes. Uh, yeah, I will need to check on that. But it's also I think it's a combination of symmetry and the coding technique, like the coding theory. For the OPIF, I think there are like older construction that yeah, I'm not sure. I need to look into it. Sorry. Yeah, I haven't yeah, I forgot about this part quite a bit. Hello. I think it's the like more practical evaluation, like the running time and such. For the yes, you can actually use the variation of OLE that I mentioned earlier, which is the vector version. The VOLE is actually the vector version. But I think the OKVS, the step of encode and decode need to be online. But you can actually set up a lot of stuff beforehand to make this efficient using vector OLE. So vector OLE is basically similar to the OLE, but you can have X as a vector of alignments instead of a single alignments. And this is very efficient. Oblivious PIF approach. Actually, both approach can be made malicious secure against malicious adversary. But this require more details. Yeah, for the OLE approach, as long as the setup, which is like basic OLE, is maliciously secure. Everything else is actually maliciously secure. And for the OPIF approach, you can actually make it maliciously secure, but I cannot remember the details. Yeah, so this one is you can actually prevent the version that I show here semi-honest, but you can actually prevent this two scenario. Yeah, it's require a few more like some steps to prevent this two attack. Okay, so let me go over the second part somewhat quickly because we don't have much time left. So the second part is going to be about the fuzzy PSI. So previously, when we talk about PSI, we want to find the intersection, right? The intersection means that you want to find a match between alignments in a list set and alignments in Bob set, right? But for fuzzy PSI, the idea is that you want to relax this exact match requirement. So as long as two alignments are similar enough, for example, here are the second alignments in a list set and the first alignment is in Bob set, only differ by 1 bit, right? So sometimes we may want to match this case as well, right? So this is no longer a PSI in the traditional sense. It's not intersection, but it's like finding a match that is sufficiently close with respect to a certain distance function. Yeah, so basically you want to match alignments between two sets that are close with respect to some distance metric. For example, in my slide here is the Hamming distance, right? So as long as two alignments differ by like at most I think example correctly maybe yeah, as long as the Hamming distance between alignments is say at most 1, right? Then we basically match them as the same alignments in the intersection. There are several variations before the more common like formal definition of fuzzy PSI to be developed. The first one is the distance aware PSI version. In this version, Alice and Bob both learn the result, which are the pair that match, right? So both parties learn A and B whose distance is less than t, for example. The problem is that the technique that they use to construct this distance aware PSI is basically very straightforward. Basically, they just find a way to test for the match between two alignments and then basically apply this on all n square pairs of alignments, right? Say, assume that both Alice and Bob has n alignments. This results in quadratic complexity, which is which make the protocol does not work on large sets, right? And they actually construct a better technique for in using like absolute difference. But the one for Hamming distance is actually inefficient. It's also has a weakness in that both parties actually learns outputs and learn as a match pair, right? So there is no variation for this version. Another variant of a CVS PSI that actually exists even before this this definition is the private record leakage. But they actually study more of trade-off between the correctness and efficiency rather than guarantee the correctness as in most PSI, as in most MPC or PSI that we study. Basically, there are a percentage of false positive, say like 20% or something like that, which is not as good as we want. This two definition actually does not require anything about the sets, so there is no structural assumption that we will focus on later. So in order to get linear communication, it's actually pretty difficult because when you have in alignment, the worst case is actually they all match, right? So in this case, you actually need to test all n square pairs. And as a result, the computation or communication may be too large for practical use. And a lot of construction in fuzzy PSI actually try to restrict it to the case where the match is at most 8. How do we do that? Basically, use some structural assumption. Basically, we assume something on the structure of one or two sets that can imply that the number of matches is not too much, and we can actually get linear or near linear communication. Yeah, so the structure aware version is so the variant that also mentioned is a structure aware PSI version. In this case, it's basically standard PSI where you want to find the intersection between two sets, but they assume that one set actually have a very rigid structure. For example, one set must be a union of fixed radius balls in L infinity norm. In this case, they want the efficiency of the protocol actually depend on the structure, but not the exact number of alignments. For example, if it's the union of balls, then they only want to depend on the number of balls, but not the number of points on all the balls combined. You can actually imply the fuzzy PSI from this from this structure. Basically, you can assume that the actual alignment is the center of the ball, right? And the rest are just something near the alignments, and you allow to match with something with alignments that are near but not exact, right? So this is the first variation, and they actually construct they actually have a few papers on this structure aware PSI. all of them actually focus on L infinity norm and the union of balls, but the requirement for the balls are relaxed as the construction developed. I think the first version required the balls to be disjoint, and the later version actually allow the overlaps and so on and so forth. And they actually improve the efficiency, improve the security guarantee, and eventually use this only symmetric key technique. So this is for L infinity. The first actual definition of fuzzy PSI actually come later, say 2 years ago. In this variation, only one party learned the result, and they actually define two variations of this fuzzy PSI. The standard one, the receiver actually learned only the sender elements, and the second variation, which they call FPSI with sender privacy, in this case, only the receiver only learned his own element that match. So basically, this is the more the functionality. This is the FPSI where Bob basically learned a list elements that match. And the version with sender privacy, Bob learned his own element that match. Okay. They actually construct the fuzzy PSI based on that definition for several distance metric, for example, LP norm and infinity norm and Hamming distance. In order to require that the receiver's alignments must be far apart. So what does it mean by far apart? I will talk about a little bit later. And there are several other works that follow up. There is one that improves the efficiency, but require quite a strong structural assumption that each vector must have a unique component. And the latest work, I think this one is in appear in IISc last year. Actually construct the FPSI for L infinity norm that does not require the assumption at all. So I think this is the first fuzzy PSI that has no structural assumption. But the communication and computation is not as good. Several work actually use the technique called fuzzy matching. So the idea of fuzzy matching is basically that you just want to check whether two elements are match or not, right? Or basically close with respect to some distance metric or not. You can certainly construct the FPSI using this F-match by just compare all pairs of elements, and you can construct this using several techniques. For example, you can use FSC for construction. You can use Gabo circuit to check for the F-match. You can also use like sender or receiver must be far apart. The previous work usually focus on the receiver sets, but our result is efficiency is a little bit more than linear. Yeah, there are several works that solve the Hamming distance. I mean the fuzzy PSI for work that focus on other distance metric, for example, L infinity and LP. So for the structural assumption, it's actually required for all metrics other than L infinity norm. That is basically required that if you take two alignments in one set, the distance should be significantly larger than the threshold that you want to test for. If this this D pump is greater than 2D, you can actually prove pretty easily that each alignment can only match with one alignment, one other alignments in the other set. In this case, you guarantee at most n pairs, right? And you can actually use some probabilistic approach to guarantee to find this n pairs with high probability. Basically, one technique that I use in my paper is basically try to project the binary into smaller vectors, and if the Hamming distance are sufficiently small, then they will project onto the same vectors, and you can repeat this process several times to guarantee the result. Yeah, so this is basically the idea that we have. Yeah, there are several other techniques to usually the general approach. I don't have time to go into the details, but the general approach is that you can try to reduce the potential match to a small number, and then you can apply the fuzzy matching to check for the result. Okay. Yeah, this F match, let me skip all these parts. The interesting part is that you can use F match to basically find the intersection between say set of pictures that may not be the same, right? Maybe or size or those kind of stuff. You can actually match them using this FPSI. Okay. Yeah. So if you want to talk a little bit more details about this fuzzy PSI, we can do so, like say later, because I'm run out of time, right? Okay. Hello. So should I stop here for question, or we have discussion after this, right? First part. I see. So usually when you want to apply the payload to OPIF, you cannot actually send this random numbers directly because it will reveal the payload, right? So usually two ways to apply the payload. One is you can use this together with some polynomial technique, but it's going to be smaller and smaller polynomial. In the polynomial based PSI that I use, this polynomial, the field size of polynomial must accommodate the alignments in the set, but you can just use a smaller polynomial that only accommodate the random numbers output of the OPIF. Another way is you can just apply the circuit to hide this payload further. So if you match these random numbers using the circuit, then you can actually send the payload along if the random number match, right? In this case, you don't need to review the payload. Yes, but you cannot send this payload directly together with the random numbers. Any other question? I cannot hear you clearly. Can you ask again, please? Sorry. Can you ask a little bit louder? Mhm. Yes. Mm-hmm. Yes, you can actually combine that I talk about. Say you can basically make all this definition fuzzy PSI, right? I would say you do the fuzzy PSI payload efficiently. I would say you can. So in my construction that I actually use the circuit PSI as the last step of my construction. So not the last step, but like later step of my construction. So in this case, you can technically add the payload to this circuit and then like hide it using the secret sharing and then only review it if it matches or something like that. Yeah, so it's not that difficult to add the construction. It depends on the construction that you use. Yeah, for this construction, it's actually not difficult to add the payload. Yeah, sorry, let me get to this. You're welcome. Any other question? You mean the technique? Which technique? Ah, um, actually, I don't really study the multi-party PSI in details, but I would say the OPIF can be used if you combine with some like some way to hide the intermediate result. But used directly, I'm not sure. Yeah, sorry, I'm not sure about how to extend these techniques to multi-party setting. Oh yes, quite a lot actually. Oh, in visiting. Actually, for the two-party standard PSI setting, they are actually I think most of the recent results actually maliciously secure. I would say not that much. For example, using the polynomial technique, you can actually lift it to the malicious case by about twice as much work. Yeah, I don't have the detailed slide, but this problem actually can be solved by, I think, by about twice work or less than that maybe. Yeah, but I'm pretty sure that is less than 2 times the same expense. Which structural piece? You mean this one? I think they actually get the maliciously secure that follow up also. The semi-honest version and the malicious version actually have large gap in the efficiency. Yeah, but they can actually construct the maliciously secure one.